They just say, oh, we should look at ice cream.
Oh, so the little bit thing, but you know, the meeting, it's ice cube. Same property, yes, simulation. In that discussion.
Yeah, I understand. You know, but
Well, because people are noisy.
yeah, super tricky.
Silent.
Pepe.
Hello, can you hear us better? Yes, very well. You took our camera as well, right? Well, but people will be silent during. Yes. Can you see? Right? But you're turning to the sides. I don't suppose. Yeah. Is it working? Okay, and let's just do one more test. Can you put on the microphone? Just one more test with the speaker's microphone. If I say something. Tim, can you hear Giovanni?
No.
Tim? Can you? Ah, okay, so yes, we use this one. Okay. What, just a second, I'm speaking this one.
Prova. Can you hear me? Hello? It's my voice, it doesn't go through.
Maybe it's better to use them on this, if they're on this for the father.
Can you hear us again? Hello? But can you hear Giovanni's voice?
Can you hear my voice? Good.
Okay, so I think we are all set. We start in 3 minutes or so, right? Okay, so you just say when you're ready. And what do we do? Do we do very brief introduction? Or you do it on your side and we do it here? How do we do it? Do we do a very brief introduction? Okay. 5 minutes.
Would you be able to see what you will sit there or no, we stand up. Ah, okay. We change them remotely.
Again, that's very.
Okay, so as you know, we are going to have this joint session with the quantum gravity conference in a bit. So the way it is organized is that we are going to have one talk from here, then one talk from there. For questions, we will give priority. So for
Okay, good morning and welcome to today's morning session. So if I may request people to move in the middle if possible so that people coming in can find a place. Okay, so let's start. So this is the session on quantum gravity phenomenology, and today's first speaker, it's a real pleasure to introduce him. So that's Giovanni Amelino Camelia from Naples. And he has been working on quantum gravity phenomenology for a long time, and maybe he was one of the first people to develop the subject. And he has contributed to issues like the minimal length scales which in quantum gravity, and using observations like GRBs to probe quantum gravity. And I remember one of my very first talks that I heard on quantum gravity was more than 20 years ago. And the talk was titled, "Are we at the dawn of quantum gravity phenomenology?" And I think today the title is very much the same. So with that, let's look forward to the talk. And Giovanni, it's all yours.
Okay, can everybody hear me? Also remotely, yeah? Can you hear me?
Yes, we can hear you.
Good, so it's better, do you have a way to tell us that they're not hearing?
but there's a chat. There is a chat.
Okay, and who's
And,
checking? Okay, thank you for the introduction. And so, yes, it was indeed, we are on this side of the conference, we are in some sense celebrating the last annual meeting of this cost action, which was a lot of fun. And so I thought, well, for me, it was an opportunity to think over these now more than 20 years, that make me feel very old, of course. What happened to quantum gravity phenomenology? When I gave that talk, it was at the Carpatch Winter School in 1999, and I gave it then several times over a couple of years. The field was really just starting, and it was in some sense even difficult to explain the idea. The background was the feeling about quantum gravity that was widespread up to that point. I always have, I mean, somebody I really looked up to in those days was Chris Isham. We actually were not far from each other for some time. And however, Chris nicely captured in one of his reviews the feeling toward the phenomenology that was widespread in quantum gravity in those days. But then we started to see some opportunities for at least testing plausible, however, vaguely plausible, but plausible effects that might come from the Planck scale with Planck scale sensitivity. And much more, I mean, one thing I can say, everybody can discuss whether we did a lot or little, but I can tell you that we did much more than I imagined over these 20 years. And in those days, really this idea that the phenomenology for quantum gravity could start was based on just first very heuristic or at best semi-heuristic estimates of effects. Now we have actual derivations of effects in quantum space-time toy models, like Kappa-Minkowski. And we have, as part of my presentation, I hope we'll at least hint at, we have rather mature phenomenological models for effects. So I would say over these 20 years, what I imagined in those days, I imagined that this phenomenology, this bottom-up approach, this idea of a quantum gravity research, which also starts from the bottom, whereas in those days, the only idea was to start from the top, to be very lucky and make the right guess about quantum gravity at the Planck scale, and then maybe one day come down from this fantastic intuition to phenomenology. And in some sense, one of the ideas was to create some, direction of advancement from the bottom so that the trip would be shorter. And I'd say from what concerns phenomenology and the needed contact with observations from early science, I mean, the bottom-up approach has done pretty well considering the challenges for these 20 years. Still, it didn't work fully, the idea I had in those days, because from the top, it's still very hard. I mean, people got interested, but it seems that the theories are too complex, and you will see some examples of the questions that phenomenology needs answers for. I mean, these questions appear to be still not within the technical grasp of what I call top-down approaches. And in these 20 years, quantum gravity phenomenology is now a very broad field. The number of, this is also totally unexpected with respect to what I was imagining 20 years ago. In spite of the fact that everybody's reference still is in-Radboud dispersion, and for some people, in-Radboud dispersion is all quantum gravity phenomenology, it's actually a very broad field. I will talk about in-Radboud dispersion is still the kind of benchmark for the progress of this phenomenology, but the number of opportunities that have been discovered over these 20 years is impressive. A pretty wide list is in my review, and even just focusing on astrophysics in this multi-messenger area, those who have not followed will be pretty impressed by the list of opportunities and the type of careful work that has been done both on the phenomenology theory side and on the observation side by, in particular, people in the SCOST action. And the review we produced is now, I guess, a rather good reference. So it's very broad. I have, however, 4 things on my menu today, which 3 of them are among the topics which were most discussed in this construction. And the Jago dispersion again, which I will discuss however in rather powerful language of dual curvature redshift. Then there is dual curvature lensing, which is a companion effect, another propagation effect. Then I'll talk about threshold anomalies, which is also very interesting for astrophysics. And in the end, I'll talk about, since the action is finishing, I should have an item outside the scope of this action, and I will talk about IR-UV mixing, which has not been for the kind of phenomenological opportunities it provides, was not one of the focuses of this construction, but maybe surely an important topic for other collaborations. And so let's start. Quick review of Jago dispersion, which was kind of the first idea that really made it clear that for some effect you could conjecture for the planet scale. There was data of a quality sufficient for testing it, and it's also historical. In those days, we have here Nick Mavromatos, and we were working on this in the dark rooms of Oxford University to begin with. And all we had was some semi-heuristic argument pointing to pointing to the idea that in a space-time that was macroscopically flat, there might be an imprint of quantum properties of space-time, which would amount to a time of travel anomaly of this order. Essentially, the typical phenomenological estimate, some power of the ratio of the energy over the Planck scale. And we realized that some astrophysical sources had time inequality. If we remember, beginning, we didn't know about the GRBs being so distant, so we focused on pulsars, for example. Remember, there are many types of astrophysical sources that are in some sense, in a very general sense, very good clocks, very far away. And so then we were very lucky because a few months later, it was discovered that gamma ray bursts with the Beppo-Sachs observation. It was discovered gamma ray bursts were much farther than astrophysicists had conjectured for a long time. So it was perfect timing for us. And we got rid of the pulsars, which were very hard to analyze, and we got to the gamma ray burst story. And it's a race. You want to test this idea, it's a race. So you need a good clock far away. A good clock means something which has a time scale of quality. And gamma ray bursts have all the nice properties you might desire, with the exception of one. This is fundamental physics where the laboratory is the universe. And so it's not a prepared experiment. For someone like me coming from particle physics in part of my interests, it's still the ugly word of astrophysics. My friends here will forgive me for saying this. But it's just that it's perfect, but it's not a laboratory experiment. So you deal all the time with a sort of uncertainty about the outcome, which has not to do with the quality of your data, but the quality of your understanding of the source, which you do not control. But this is also very fascinating. I mean, to have this fundamental physics in which the universe is the laboratory is perhaps on a broader conceptual scale, a significant accomplishment for this type of, the usual direction of fundamental physics, the physics that studies the more and more microscopic scales, is to adapt very strongly to the very big and unknown features of the whole cosmos. So that has been a journey which we're still doing and fighting. So I will not give detail. There are a gray part on this slide because there are some technical details which I'll omit, but if there are questions I can show. But for the understanding of in-vacuum dispersion, I guess a very useful tool, probably nothing more than a tool, but surely very valuable, are these works on the relative locality framework, where we realize that some of these models where you find in-vacuum dispersion actually were all models where momentum space was curved. And momentum space was curved in a certain technical sense, which again, I will not describe, but I can describe in answer to questions. But it's very interesting that these allowed us both conceptual understanding, but also technical advantage. We now compute what we call sloppily time delays. We compute the time delays as dual redshift, as I mentioned. And for those who are not quickly seeing the connection, I mean, just seeing that ordinary redshift in the zeta space-time is such that particles emitted with the same energy but at different times reach the detector with different energy. And what we find is just exactly a dual picture. So, for example, dual redshift in the zeta momentum space is such that particles emitted simultaneously but with different energies from a distant source reach the detector at different times, which is in-vacuum dispersion. So this was conceptually a useful tool, but still it was in flat space-time. Okay, when I say dual redshift in the zeta momentum space, well, leaving implicit that we have a good understanding, we have good formalisms to handle this. If we assume that space-time is macroscopically flat, and also the formulas Nick and I were using in the old days are flat space-time formulas, but the gamma ray bursts are in our universe, which is not flat. So technically, one of the challenges that has kept us more busy, those studying in-vacuum dispersion for these 20 years, is to understand how these results, if we use the relative locality framework, some of these results are absolutely clean and rigorous when you assume space-time is flat on macroscopic scales, but how these results are changed if you work in a curved space-time. And to deal with both curvature of space-time and curvature of momentum space together is really a mess, even from the point of view of just developing phenomenological models. It's very hard. We discovered it was a conjecture. Max Born in 1938 already conjectured that this might be needed for quantum gravity to be able to deal both with curvature of momentum space and curvature of space-time, but that somehow mystical encouragement that does not provide the tools to handle it. The phenomenology has managed to make progress thanks to, well, preliminary work by Nick Mavromatos, John Ellis, and others, but most efficiently in some work by Jago Kiran, where with a compelling heuristic argument, they produced a formula for how basically this energy-dependent time delay would interface with the curvature of space-time. And most phenomenology, 99% of data analysis, for example, they all use this Jago Kiran formula, which actually is proving to be more powerful than even initially imagined. But one of the new challenges for this phenomenology is to understand what are the alternatives. Actually, we do find constructively, I would say, in the SR models, for some models of the curvature of momentum space, you actually find the Jago Kiran is not heuristically motivated, it's just derived constructively without any assumptions for some assumptions about the curvature of momentum space. I mean, not assumptions technically, but you have some assumed structure for momentum space, and you just get the Jago Kiran formulas, but there are alternatives, and this is now one of the, I would say, hot topics in this research line. If you have broken relativistic invariance, you can have the Jago Kiran formula, but really you can have anything. If you break più vicino, if you break Lorentz invariants, you break symmetries, anything goes. So we are noticing more and more terms that could be alternatives to the Jago Kiran ansatz. But there is no limitation in principle. You need a specific theory to analyze and derive the effect, but you cannot constrain the form of the redshift dependence using the Lorentz invariance. It's broken because when you break it, it's broken. We have some direction of investigation, which I will say more later, so I will just keep on now, which is the curvature induced effects. And then we have this deformed symmetry. So if this invariance is not broken, but just deformed, then instead we are discovering actually Domenico Frattulillo later today here will give a final word on this, because we have the most general DSR compatible formula for the redshift dependence, and we discovered it only has 3 terms, which is worse than 1, but better than infinity. So we will deal with the 3 terms from the DSR side. 2 had already been discovered, but we recently became able to do the most general analysis. So this is one of the frontiers. This is one thing that if you have a favorite top-down approach, assuming there is Invariant dispersion in your top-down approach, which will not always be the case. But if you have it, then the real important input for phenomenology will be this redshift dependence. But this will require the top-down approach to be able to describe a physical question like propagate a particle when macroscopic curvature is F of W. Because that's where the measurements are. Let me pause a moment on these curvature-induced effects, which are another kind of new frontier, because the Jago Kiran formula, which has been very influential, as I mentioned, is not of this type. So the Jago Kiran formula is a time delay formula which gives you a time delay even in the flat space-time limit. Now, from the deformed symmetry perspective, what we are dealing with is probably a quantum group or something similar to quantum group, but the way we model it is through of algebras, basically. And in order for the effects to be still present in the, so say you have the Invariant dispersion in a quantum version of the Sitter symmetries. A quantum group, Q de Sitter could be, some people in the audience here in Rijeka are experts of Q de Sitter. And say you have, as you have in Q de Sitter, you do have Invariant dispersion. Now, will you have Invariant dispersion in the flat space-time limit of this picture? Well, that is what should come out of an Nijmegen contraction of this de Sitter type algebra to the corresponding Poincare limit algebra. And typically the contraction of such an algebra is a Lie algebra. So this was stressed in particular in a paper that we did with Artem Starduksev and Lee Smolin many years ago already, 2004. And where we noticed that most of the arguments leading to quantum groups in quantum gravity, they all had in common that the Q deformation scale, the quantum group parameter, it's not a scale actually, in the quantum group Q is adimensional, but is obtained by combining the Planck length and the cosmological constant, say, if you assume the Sitter is, if you call the parameter of the Sitter, you call it cosmological constant, they combine the Planck length and the cosmological constant in such a way that when you do that in Nijmegen contraction, the quantum group features disappears. So in this case, you would have Invariant dispersion when you have curvature macroscopically, but in a certain form that would disappear in the flat space-time limit. And interestingly, there are other arguments, one more inspired from the loop quantum gravity intuition by Rovelli Bianchi also motivate, I would say at a semi-heuristic level, but rather compellingly, that a quantum group parameter Q coming from quantum gravity should be given by this function of the product of the Planck scale squared with the cosmological constant. And in all such cases, you would expect, if you have in vacuum dispersion, and I repeat, if Q de Sitter arises in your framework, if the quantum group Q de Sitter arises in your framework, chances are you will have in vacuum dispersion, but it will be of this particular type, curvature induced. So such that in the limit of flat space-time it will disappear. And we have now some phenomenology of curvature induced, even for the broken symmetry effects. I repeat, the Jago Kiran is not curvature induced, so we need to find a new reference for curvature induced effects in the broken symmetry phenomenology, which is not easy because maybe it's we should try, because we see only so many terms possible, and so we can give examples, but there must be, once again, one such combination of terms that the expert astrophysicist will look at and consider most deserving of attention. We just are able to analyze this broken symmetry curvature induced effects rather in detail right now. And what Domenico Frattulillo will say later today is that from the DSR perspective, we have a full description of curvature induced. The most general formula for DSR curvature induced in vacuum dispersion, and it is a two-parameter formula. One of the parameters must be set to 0, one of the most general formula to get curvature induced. So this is just an example. I mean, I don't know the broader scheme or broader picture, though this will be perhaps irrelevant, but it gives you a sense of what are the type of issues that phenomenologists must struggle with. I mean, we are in a real universe with its curvature, with its bumpiness, with magnetic fields, and so we cannot use charged particles to do these studies, which would be very useful. And our daily routine is just fighting all these enemies in some sense. I will say very little about dual curvature lensing, but it's just basically the same effect rather than, as the name says, when you have a curved momentum space, there can be some longitudinal, some effects in the direction, in the plane, say in the plane of time and the direction of propagation. And those would be in vacuum dispersion, and those are dual redshift. But when you have a curved momentum space, chances are you will also have dual lensing, and this is an effect in the plane orthogonal to the propagation direction. So what produces are artifacts about the direction. So instead of looking for an angle, in the xt plane, which is time delay basically, you look for an angle in, so it's a misdirection in the yz plane, whereas the vacuum dispersion is misdirection in the xt plane. So it's very similar. The phenomenology was stuck at the beginning for a very long time, because for this, you need very accurate directions rather than accurate timing. And for astrophysics, accurate directions are there. But I'm hopeful that at least its phenomenology will start now with multi-satellite telescopes, which promise to give us a much better direction in observation of some astrophysical phenomena. So this is just an appetizer, a hint that maybe I keep this long, I'm still alive in 20 years. If I still have voice, I can say that dual gravity lensing did many progress. Threshold anomalies. Threshold anomalies are basically forbidden in DSR. If you deform symmetries, you mean basically it's not that they're forbidden, but you will get them at the scale where you put the new physics. So that's not what we want. We are doing a phenomenology where the scales we access are very distant from the scale, which is our target. So let's say the threshold anomalies are just for the broken symmetry, but there is a very interesting phenomenology coming out of it. I remind you quickly how it works. For example, we have some features in astrophysics which are connected to the threshold energy requirement for gamma producing A plus A minus. This is typically when we observe a high energy photon from a distant source, and we know it traveled in the background of cosmic photons, and those background photons are the target to make electron-positron pair. And of course, if you have the unsharpness of the particles being modified, you will modify, I will skip the details, but you will modify your threshold formula for electron-positron pair production in a characteristic way. And this again, it works out to be one of those rare cases where the conjecture plug scale effect is actually observable in astrophysics. And the data situation continues to be very interesting. The most famous threshold anomaly, which has a beautiful history, which also teaches a lot about doing fundamental physics using the universe's laboratory, is the GZK cutoff. There is a similar threshold anomaly, which actually Sui and I studied already 22 years ago. But there was a Japanese, somebody before us did. I'm sorry, I don't have references on this slide, and I should credit a Japanese colleague whose name I'm now not remembering. But certainly, Sui and I in order these results in 2001. And this is the very big opportunities, because in this case, the cosmic ray protons we observe have energies of 10 to 20 electron volts in some cases and above. And there is a threshold anomaly for the bind production that you can quickly analyze and robustly analyze. And the story of this possible threshold anomaly is very funny, because when Sui and I wrote this paper 20 years ago, there was considered to be lots of evidence for the threshold anomaly. And then at some point, about 10 years later, the threshold anomaly had completely disappeared according to some analysis. And then now it has reappeared again in some sense. So this is the difficulty of the universe's laboratory. And so also, if you ask me, I can explain how these big changes are arising. But that's still an open issue. Then we have an opportunity, just to say also to more formal theories, there is a real opportunity. There is something we still need to understand about this possible threshold anomaly. And similar for the electron-positron pair production by photons, which I mentioned before, not only there are opportunities, but the data are going to be of much better quality in the coming years. There are two very different opportunities. There is the one that was most studied over the last 20 years is for TeV blazars. So for photons of, say, 10 TeV, 20 TeV energy coming from redshift of, say, 0.3, 0.4, 0.2, low 0.3. That's where, if you use what some experiments, some observations suggest is the levels of far infrared background photons, these 10 TeV, 20 TeV photons should be absorbed by that background, and they are not so absorbed. So that's another kind of small crisis. The universe is less opaque to multi-TeV photons that it was initially assumed. But again, the universe is a laboratory, and we don't know who to trust, because it's also very likely, probably the most likely explanation. Every other explanation before quantum gravity is always more likely, actually. And the most likely explanation is that the measurements, they are indeed very difficult, these measurements of the far infrared background. So probably the answer is this, that we do not have enough quality of the measure of the far infrared background to actually have robust prediction of how much, okay, the universe should be. But there is, there is a crisis. There is something to be understood here, a real opportunity for, it's not just, well, this we can measure. That's where some measurement is not giving so far a nice picture. And similarly with LASO, now we are observing much more energetic photons. The background photons, the background there is much better understood, but the universe is a laboratory, so it happens that when you understand the background, because there is lower energy photons are relevant for higher energy. Lower energy photon background is relevant when the high energy photon traveling is of higher energy. LASO observes at higher energy, there we know the background, but LASO is still not able to find sources. So we don't know from how far we see. But all this is going to soon. Something about infrared ultraviolet mixing very quickly is infrared ultraviolet mixing has not been a topic of this course action because so far very little implication for astrophysics have been conceived by phenomenologists, but this could be the topic of another course action, for example. One of the topics, and surely is a key target for phenomenology, where also more formal quantum gravity researchers could help. It used to be a very hot topic in top-down approaches some years ago. It remains very significant for phenomenology. It's probably a very generic prediction of quantum gravity to have some infrared ultraviolet mixing. If you think about it, Hawking radiation, or actually the information paradox and the fact that entropy scales with area. If you have a theory where entropy scales with area, then you have infrared ultraviolet mixing for sure, because you have, you have infinite ultraviolet features, but you have crisis which goes worse and worse in the infrared. So this should be a very generic prediction of quantum gravity. At least of all models that have entropy scaling roughly with area. And you also find it again in some quantum space-time Thom models. You find it now constructively. There's a famous story, particularly in the canonical non-commutativity of space-time. You do your, the point is that the canonical non-commutativity screws up renormalization, and when you renormalize the theory, you're left with the renormalized theory, which has infrared features, which are very significant. That's a kind of a reference calculation showing how infrared ultraviolet mixing might arise. Why is phenomenology interested? Well, once again, for totally different reasons, but its own shellness is the propagator really that is, at least in this toy model canonical quantum space-time, canonical non-commutative space-time examples, is really the propagator that gets primarily affected by this IR UV mixing. So again, it's physics with a deformed own shellness that comes from this infrared ultraviolet mixing. But now, of course, the features that you look for are features that pop up in the infrared, and there are various candidates for these infrared effects coming from different models. The one possibility that hard infrared ultraviolet mixing has a 1/p² Hall, and that's, you cannot do much phenomenology with it. A Hall is not so easy to deal with phenomenology. You just, if no disaster happens, a Hall manifests itself as a disaster. So you improve your phenomenological bounds on these forms of infrared ultraviolet mixing by just going at lower and lower momenta and checking that no disaster happens. More interesting are other softer forms of infrared ultraviolet mixing, which I illustrate on these slides. And they have, these are, for example, significant implications for cold atom interferometry that has been shown very definitely. And in astrophysics, these things will affect things like the Chandrasekhar model, where the on-shellness plays a very detailed role. Okay, so this was my menu. Now, let me close a few minutes on the. This was the menu, and it's a very general perspective. Some directions, as I mentioned. The interesting thing of this menu, of course, you have the English version of ogni scarafone bello va a una sola. There is an Italian expression that every ugly person is beautiful for their mother. Ogni scarafone bello va a una sola. This is Neapolitan. And I mean, of course, this just comes to mind, but every speaker will say that what he tells you is very interesting. So I tried to avoid that, but I was just saying that the menu is very interesting because every Scarafone is beautiful for his mother, but also because there is something new happening in all these directions. I will close now with the invariant dispersion update, but I mentioned that for dual gravity lensing, really a totally new window is opening because with multi-satellite telescopes, we will enter a totally new window. And they are going online. So this is coming. And for threshold anomalies, if nothing else, LASO is probably going to revolutionize the field. And for IRUV mixing, if nothing else, surely the cold atom interferometry is one sure bet. If you want to bet, there is a classic law that every field should improve by a factor 10 every 10 years. But really the only ones who are doing it are those doing cold atom interferometry, and they will keep doing it apparently. So the quality of data for at least that branch of IRUV mixing is going to improve at the pace of a factor 10 every 10 years. You can bet your money on that. So these are all menu items that look beautiful to me, and this might not be very objective, but they are items where improvements are coming in the next years. Let me close with some remarks on where in vacuum dispersion, the more mature, certainly, phenomenology of this sort stands. Well, something that I also didn't imagine. We didn't know really, in 1999, we didn't know how gamma ray burst at high energies would look like, because we only had, at that point, telescopes which would see gamma ray bursts at much lower energies than the one inferred from this graph. What we have discovered is that some gamma ray bursts, they are really very efficient for testing hypotheses like in vacuum dispersion. Look at this particular burst. This is a burst from 10th of May of 2009. And there is one particularly energetic photon of about 30 JeV, which we observe in very close coincidence with the busiest. Now, the signal has also a rather busy part between 1 JeV and say 5 JeV or something like that. And the busiest part of the signal between 1 and 3 JeV, say, is very good temporal coincidence with the 30 GeV photon. Of course, the universe is a laboratory, so many things the source could do that would affect what I'm just going to say, but it looks very unlikely that there was in vacuum dispersion at a scale larger than, say, this alpha second scale that we have in the bottom here. It would require a huge conspiracy for that to happen. So from data like this, and we measured the redshift. This particular gamma ray burst, if I remember correctly, is a redshift of about 0.9. So it's we measured the redshift, we know how far it is, and we have some reasonable up to conspiracies, let's say, modulo conspiracies. We have a case that can bound how much in vacuum dispersion can occur. And actually, if you put the numbers, even just very simple, there are more sophisticated techniques that some astrophysicists are using, but if you just limit yourself to this very simple and therefore robust argument, you actually find that you are testing Radboud dispersion just at the level of the Planck scale in the linear formula, and that's even more than I expected. Something interesting is, well, and I have some others. I mean, this is probably the best. This burst from 2009 is probably the best, but I have other examples I could show of very similar, robust cases where you don't see the effect at the level close or of the order at least of Planck scale. Actually started with work by the group of Bock and Ma, no, but actually already Alice and Mavromatos and others, I think also Dimitri was in those papers, or don't remember you. Okay, I don't have references on some guys, but there was whereas some were looking at single gamma ray bursts and trying to make observations like the one I just made. Actually, the first ones were Alice, Mavromatos, and others, but then more determinedly, let's say, a group in China led by Bock and Ma. The idea was, well, this is a redshift-dependent effect, and as we described in our early paper, I mean, the redshift dependence is really the key. We don't know what redshift dependence could be, but we can take as reference the Jago Kiran ansatz, and let's look. So what in the end, through the work of Bock and Ma and others, became a recent standard for doing this statistical analysis, to take photons which had emission of energy greater than 40 GeV, and to plot their delta T with respect to the first peak and low energy of the signal. So it's basically, it take more time than I have to explain in detail, but you're basically putting together different GRPs by only using their most energetic photons, and you look for a correlation. Is actually the data show to some extent. And I circled 2 points because the red point is actually the gamma ray burst from May of 2009, which I was mentioning, and in fact is off the correlation. And the green point is important because it's actually a prediction, because when Bock and Ma and collaborators started to make these graphs, that point was not yet observed. So it has a kind of, even so far, very moderate but successful predictivity in this approach. Last item, neutrinos. So finally we have our chairman Julia was on the neutrino analysis. So she just gave me 1 more minute. It was 2 minutes, became 3. Okay. It would just look like a funny joke that the chairman gives you an extra minute. But she didn't do it. It's just my mind. But doesn't work well. So neutrinos, why? Now we have neutrinos. That's something I didn't figure out, at least how important it could be. We have neutrino telescopes, and we have robust evidence that we are seeing neutrinos from outside our galaxy, and most astrophysics experts, when I started to realize that observing neutrinos from gamma ray burst would be powerful for the phenomenology, they were telling me, and the papers were saying, that IceCube should see 5 or 6 GRB neutrinos per year. Okay? Some in the audience will remember these predictions. Well, IceCube has taken more than 10 years of data and has seen not a single GRB neutrino. So this is another crisis like the one of the far infrared background. So is this a mystery, or is it just that our astrophysical models really are not reliable to the point of predicting how big, how frequently we should observe GRB neutrinos? The answer is obviously, most likely, the models need to be improved. However, there is something to be understood. And certainly in Radboud dispersion here could be relevant, because IceCube looks for GRB neutrinos by tight requirement of time coincidence between the neutrino and the GRP. But of course, if you have a time delay acquired by the neutrinos, you wouldn't see them in that window. So what we did in a series of papers, one appeared very recently in the June issue of Nature Astronomy, is to look for correlation between neutrinos and GRBs, not with coincident time, but with the time of arrival difference governed in this exploratory study again by the Jago Kiran ansatz. And it was kind of interesting as we look at the data that we had available. I should make Giacomo Rosati will talk later today. Tomorrow you speak. Giacomo will give the details of this analysis, but we find a quite impressive, certainly preliminary, just a few events, but there is an interesting case that we could build, preliminary case, that this idea of looking for correlation between neutrinos and GRBs, but with a time delay, they're certainly not there in coincident times. But if you input the time delay that we could expect from this in vacuum dispersion phenomenology, then a rather striking correlation arises. And this again, I mean, I will not dwell much on how significant this is correlation. We have statistical tools in our paper if you're interested. In our paper, this of course is described in detail, but really on the topic of this talk, this is another area where we will have much more data. And if, again, you're not bored and I give a talk like this in 10 years, I will be dead. Wow, if you ask me. In 10 years, I will have many more neutrinos on this line. And so this correlation will either disappear or become very strong. And on this, I stop because the chairman just threatened to kill me. For those who are not here, I should relay, and there are witnesses that the chairman, when threatened to kill me if I didn't stop. So of course I stop. Thank you.
Thank you for being on time. And I think we will give priority to questions from the virtual audience. So, Tim.
So we can do questions from both places. So let us start with Madhavan, then here.
Yeah, so I had a question about there was an earlier paper by John Collins and Alejandro Perez and Daniel Sudarsky, and many of these effects which were preferred frame or Lorentz violating, etc., they managed to argue against them, saying that this was another fine-tuning problem. So I just wanted to know which of the particular things you talked about would evade these theoretical arguments.
Thank you. So the main one of the main conceptual points here in my presentation was the difference between scenarios where you break Lorentz invariance and scenarios where you deform Lorentz invariance. Some studies, there were also other studies. Myers was one of these studies. Let's check. Anyway, I should have more references on these slides. But anyway, there are several studies that have observed that if you break Lorentz invariance, basically renormalization is screwed up and you need very high fine-tuning in some sense, very simple-minded description. Results do not apply to the deformed symmetry case, but on the deformed symmetry case, what applies is that we are still learning how to do. There are proposals, but we are in the phase of understanding still what is the correct way to do field theories with these deformed symmetries. So quantum field theory with broken Lorentz invariance have this a fine-tuning problem. Some will claim. Some will claim. I'm generally speaking, yeah, then you can answer, but I'm generally speaking, because as a phenomenologist, however, and actually, as you might know, I have been a strong advocate of the deformed symmetry scenario on the conceptual side. But as a phenomenologist, fine-tuning, I mean, I see so much fine-tuning in the universe. So an argument that disfavors the phenomenology on the basis of fine-tuning, doesn't interest me. But for the more formal theories, an assessment is that there are claims, and Nick Mavromado will argue against it, but there are claims at least that quantum field theory with broken Lorentz invariance requires high level of fine-tuning. For deformed relativistic symmetries, there is no such claim, but maybe it's just because we still don't know really how to do quantum field theory. So in both cases, quantum field theory is a challenge, but in neither of them is a challenge as we discourage a phenomenologist, because fine-tuning is what? Is a perversion. And not knowing how to do something is not a good reason not to do phenomenology. You know, it's a different mindset with respect to more formal approaches. Will let me?
Yeah, maybe you will let Nick comment quickly, or do you have more questions there?
There is one more question here.
Yeah.
Okay, so maybe you go first and then Nick.
Well, my question will be the following. What are the criteria to choose the dispersion relations to be tested? That is, of course, the main criterion is that in some limits they should reproduce the usual Lorentz invariant ones. But besides of this evident criterion, what are the possible ones?
Well, actually, this is easy. The answer to this is easy. Let me do it in flat space time so that I really know. So, for example, so the first answer is it must disappear when you take the Planck scale to infinity. And what you need in phenomenology, in this phenomenology, you don't need the exact formula. You just need the leading order correction. This is very interesting for formal physicists, because how do you know it's the right formula? But for phenomenology, you don't need the right formula, because we will be so lucky if we catch the leading order. So what I'm writing in my slides do not have the presumption of being, actually in the toy models that I prefer, like this Kappa-Minkowski space-time, we can constructively compute this modification to the shell, less than time delays, and they depend on an exponential of the ratio between energy and the Planck scale. But this exponential appears in the formula in such a way that when you take the leading order, it's actually a linear term. So the criteria, of course, is that the effect must disappear in the limit of Planck scale going to infinity. The idea to be understood by more formal theorists is that we only need the leading order. A phenomenologist will not pay attention after you give a formal talk and you show me the leading order. Then you say, but now I show you what the exact formula is. I will go get a coffee when you show me the exact formula, because I cannot test it. It's intestable. You know, the only chance we have is to test the leading order. And the leading order we are assuming is the leading order of an analytic formula. Of course, you could have worse things, but we're assuming the leading order is an analytic formula, so we are assuming the leading order will be some power of V over E Planck, as you see in these formulas. And again, all the models we are able to actually constructively analyze, they give this, they give analytic corrections which have a leading order which is either E over E Planck or E square over E Planck square. So we don't make any selection, really. We don't need to do one advantage of this phenomenology, which is desperate. You know, we are looking for such small effects, which is always a disaster, but is an advantage because we don't have to actually choose formulas. Because when you only need the leading order, you will test all the leading orders you can test, independently of who proposes who.
Okay. Can we do one last question from you?
Sure.
from there, yes, then we should move on, but yes, one quick one probably.
Okay.
Very simple one. What about diffeomorphisms? Is there some type of effective action that produces these effects, and that is diffeomorphism invariant, or do you simply give up diffeomorphism symmetry?
No, the idea is not to give up with the diffeomorphism invariance. It's just a tough topic. So what we need here is some sort of, and the only example that I have seen myself worked out to the level of detail for me to make sense is non-commutative geometry. What we really need is a notion of like a generalization of Riemannian geometry, where locally, instead of being locally Minkowski, is locally quantum Minkowski. And what we all think, I mean, I don't know of anybody who would give up diffeomorphism invariance in the quantum space-time research, is not that we want to give up diffeomorphism invariance. Surely we will not have classical diffeomorphism invariance, but we probably are dealing with quantum geometries, and so we need a new notion of deformed diffeomorphism invariance, which applies to geometries which are quantum curved in some sense. And what is clear to us is that it must be locally not Minkowski, not classical Minkowski, but some quantum Minkowski. So quantum Riemannian. I don't know if this makes sense, but we will discover that surely we are not giving up diffeomorphism invariance, but we are not imagining classical diffeomorphism invariance to be compatible with this. If we have locally quantum Poincaré or quantum de Sitter, to have the quantum group Q de Sitter applied to constant curvature geometries, then we will have some quantum version of diffeomorphisms applying to this. There is some research, I think the West group in Austria did some work on this when West was alive. There are some works on this idea of a deformed diffeomorphism, kind of a quantum group version of diffeomorphisms, but nobody has gone far enough for me to say that there is a compelling candidate. But what I can reassure you that we do expect diffeomorphism invariance, some form of diffeomorphism invariance to arise.
I think Nick wanted to comment very quickly, and then we can move on quickly.
Well, I will. First of all, as an early comment, do not mix, please, the DSR with the modified special relation. You may have spontaneous breaking of Lorentz symmetry through background, which we have, which is perfectly, you can construct an action which is diffeomorphism revised, but the background breaks. Now, I want to come back to this renormalization group argument. This is incorrect. In condensed matter physics, you have an explicit breaking of Lorentz invariance, and of course, there is no fine-tuning, right? So in any condensed matter system, you have the Debye frequency, which is whatever you would call the ultraviolet cutoff. The speed of light is the sound speed, but then the system is not a relativistic convergence. The mistake that they claim on this is that they did Lorentz invariance renormalization argument to a non-Lorentz invariant or spontaneously broken thing. That's what I wanted to say. And to finish, the cutoff, since you mentioned the Pirans and Jacob formula, if the cutoff, if you break Lorentz invariance through defects, as we did it originally, then the factor 1 plus z is not there because you have a redshift-dependent density of defects, which because it's a linear defect cancels it. So there are more general formula, as you said, than this. This Jago Kiran assumes a constant ultraviolet cutoff for gravity. That's what I wanted to say. And to answer Christoph's better question, yes, there is the diffeomorphism invariance if there is spontaneous breaking of Lorentz. That's all I mean.
Thanks. You want to say something, or we should move on, in fact?
Yeah, I think we need to move on here. So let us thank Giovanni once again. And let me welcome our next speaker. So while he's setting up, so it's Jan Plewka from Humboldt University and previously at the Albert Einstein Institute in Potsdam. That's a long time ago, yes, but is well, or rather I know him the best for his work on the ADS-CFT correspondence and spin chains. And since then he's changed, well, now he's turned his attention towards gravitational waves, and today he'll talk about applying some of these techniques to calculate gravitational waveforms.
Thank you. So wait for the screen to come up, but let me already use the opportunity to thank the organizers, in particular Renate and Frank, for inviting me. Also Timothy for last-minute help with the computer system, which I hope is going to get started now. One slide up. Can I do this? Oh. At any rate, so it's quite ironic because this is the first time I'm speaking at a conference for quantum gravity explicitly, and I think I spent most of my career working on aspects of quantum gravity. But now, in the last 3 years or so, I turned my attention first time to classical gravity, and as a matter of fact, I think also for the first time in my career, I have computed things which are actually measurable, and I must say it's a lot of fun. So I'm going to speak about high precision classical gravitational wave physics from a worldwide quantum field theory, and that's based on a series of papers I've been working on with a great group of collaborators back in Berlin, namely Gustav Ure Jacobsen, who is a long-term postdoc financed through our RTG, and 2 PhD students. Gustav Mogul is the long-term postdoc, and Gustav Ure Jacobsen and Benjamin are both PhD students. The first Gustav just graduated, and we've also had some papers together with Jan Steinhoff from the Albert Einstein Institute, who brought in the gravitational wave expertise into our group. So let's just start, and that was why we fought so hard for this computer setup with Timothy to get this movie going. So with this little movie, I want to show you sort of the content of my talk. These 2 black dots here, you can think of them as 2 black holes which are flying past each other at, 40% of the speed of light somewhere in our universe, and because their masses are being accelerated, they emit gravitational waves. And the goal will be to compute both the waveform, that is the far-field waveform, which is the thing we can in principle observe in gravitational wave detectors, although of course the 90 or so events that we've seen so far originate from bound state systems, so mergers of 2 black holes or neutron stars which encircle each other for a long time and then fuse. And the second observable that one can compute, and that's what I'm going to put a lot of effort in, is essentially the scattering angle. So the change of momentum from initial to final states in that process. And then we'll also look at spinning degrees of freedom. So we'll also look at the change of spin in that setup. So why is this interesting? Why is this relevant? Well, first of all, we have to provide very accurate waveforms for the new generation, the 3rd generation of gravitational wave detectors, which are scheduled to go online in the 2030s, and they will increase their sensitivity by a factor of up to 100, and also extend the frequency range of their observations. And that entails that the present state of the art of the predictions from the standard model of gravity, Einstein's theory of gravity, are not sufficient, and we have to go well beyond the existing predictions. Of course, in doing so, very similar to high precision studies in quantum field theory within the standard model, this, the justification for doing this is to perform high precision tests of our standard model. So Einstein's theory of gravity, testing it in strong field regimes. We can also study questions related to black hole formation and populations. Of course, neutron star properties are also hiding here, and potentially one may even be able to see signals beyond the standard model. As I said, to date, some 90 such merger events have been observed in the LIGO, Virgo, Kagra observatories, and these are plotted here in this very nice plot where you see the solar masses of the 2 constituents and then the emerging fused higher massive black hole or neutron star that emerges. So, as I said already, the 2 main players in this scene here are black holes, which of course are only characterized by their mass and spin, as well as neutron stars, which have more degrees of freedom, a radius, tidal deformability parameters, and so on, which are the highest density mass objects in the universe, and they serve as sources for these gravitational waves. The situations that we have been able to observe so far are the bound state situations where we have a very long end spiral phase, sort of this blue phase, in which continuously gravitational waves are being emitted. That's why the frequency rises. They come closer and closer to each other until they merge and then ring down into a stationary phase. Our work is focusing on this in spiral phase, which is the longest phase in the the history of that system, in which weak gravitational fields apply, and a perturbative setup where you look at the metric tensor as a fluctuation about flat Minkowski space is the correct description. And this is, of course, exactly the setup that we've been studying for many years in perturbative quantum gravity, and sort of that connection is the base of our approach to use these developed techniques to study perturbative quantum gravity now for the classical system, for the classical two-body problem. And a particular incarnation of that is the worldline quantum field theory approach, which I want to introduce to you. So just as in the Newtonian case, the general relativistic two-body problem comes sort of in two flavors, either the bound or the unbound state. For the bound state, the natural expansion is actually not just in Newton's constant g, but due to the virial theorem, this is linked to the velocity. So one does a so-called post-Newtonian or non-relativistic expansion here, which goes in powers of g and v squared. In the scattering scenario, which is the scenario I want to focus on, you can work exactly in the velocity and just expand in weak fields, so essentially in a power of g expansion, which one calls the post-Minkowskian expansion. This latter thing is, of course, the situation which is closer related to quantum field theory, where the scattering experiment is sort of the paradigm of all our descriptions. And I will focus exclusively on that case, and then the end comment on how we can use results from here to also infer information for the bound state system. So how would you set up such a problem traditionally? Well, first of all, we need a description, an effective description of the black holes or neutron stars. And as long as they are well separated, meaning that the separation of these two objects is much larger than the intrinsic sizes, so the Schwarzschild radius of a neutron star, a point particle approximation is a good first order description. So we just have the point, I'm missing the mass term here, the point particle, and that is coupled to bulk gravity plus some gauge fixing constant. Now what you would do, you would look at the equations of motion, so these are Einstein's equations and geodesics equation, and then set up to solve them perturbatively. As we're looking at this scattering scenario, we would start out with a zeroth order situation where we just have straight line trajectories. So this would be the blue trajectory here. And then you systematically, in a G expansion, compute the deflection corrections. And of course, on the gravity side, you start out from Minkowski space and then compute the emitted radiation also in powers of G. However, you might not be, or you certainly are not interested in the exact trajectories and also the gravitational field everywhere, but you're interested in the far field waveform, so the 1 over r part of the metric, so this blue tensor here. And also this would be what I showed you at the beginning, these, the waveforms emitted, and then also in the dynamics, so the impulse, the change in momentum is an interesting observable that you want to compute. Now, the way we approach this problem is by translating this perturbative solution of the classical equations of motion to a diagrammatic problem in a sort of hybrid quantum field theory, which has a worldline part described by one-dimensional Q of t, which describes the black holes and neutron stars, and the bulk gravitational action. So one simplification that you can do, you introduce an Einbein on the worldline, and go to sort of a Polyakov type formulation of a problem to linearize the coupling to the metric and the graviton. So that would then be the leading description. But of course, there are more degrees of freedom, finite size effects, but in particular spin effects. So you would want to also describe the spin of the black holes or the neutron stars, and then also tidal deformabilities. And I'll tell you in a bit how you sort of augment this worldline action to also capture the first layer of these effects. Now, in our WQFT prescription, what we do is we, of course, make the same ansatz of a deflection and a gravitational fluctuation about flat Minkowski. But then we perform a quantization of these blue fields, so of Z and H, and just look at the tree level contributions to the one-point functions. Because the one-point functions, the vacuum expectation value of H and of Z, solve the classical equations of motion in this particular background, the straight line background, and that's all we need in order to set up a systematic expansion, and we can also directly focus on the observables we're interested in. In doing that, we can port advanced quantum field theory techniques, in particular multi-loop integration technology, to this classical gravitational physics problem. So let's have a little bit closer look how this perturbative setup looks at. So as I said, we have these two quantum or fluctuation fields, the blue ones, Z and H in the problem. For the world line, we have quadratic, we have a second order time derivative here, so that's why we pick up 1 over energy squared, omega squared propagators on the world line. So these are the world line fluctuations. And then in the bulk, of course, we have perturbative quantum gravity. So we expand out the Einstein-Hilbert term in this weak field approximation. We pick a gauge, the delta gauge, and then, of course, you start out with the well-known graviton propagator right here, and you have an infinite series of graviton interactions in the bulk. One important technical detail, which I don't have time to get into in these 30 minutes, is that the nature of a problem forces us to work with a Schwinger-Keldysh type or in-in type formalism, because we have dissipation. When you have the ingoing situation, you have no gravitational waves and you have no Z. However, in the final state, it's clear that you have shifted, so the deflection Z does not decay to zero at infinite times, and also you've emitted gravitational waves. So you don't prepare the in and the out state, but you only prepare the in state and you want to know the outcome. So at the end of the day, all that happens is that you're advised to take retarded propagators instead of Feynman propagators, and you can work with the standard Feynman rules you extract from this description up here. But there's a longer story in order to prove that that is correct. But in hindsight, you could argue it's obvious, because all I'm doing is I'm just setting up an efficient way of solving equations of motion, the classical equations of motion. And there, of course, I would always use, for causality reasons, the retarded propagators. How can we now include spin on the world line? And there we have a very nice description, which actually is inspired by string theory. Namely, we capture the spin degrees of freedom of the black holes or the neutron stars by adding anti-commuting fields, vectors, on the world line. And if you take n flavors of these, you are able to describe up to spin to the power of n interactions. And it turns out that at least up to n equals to 2, which allows you to describe spin orbit and spin-spin interactions, the resulting theory is an n equals to 2 superparticle coupled to a curved background. And that is exactly this blue theory here, which I'm writing down. So the black and the blue together are exactly the n equals to 2 superparticle action with fixed coefficient here for the r psi to the 4 term. And these psi's encode the spin tensors of the black holes and neutron stars as follows. So the spin tensor is just given by essentially this bound state of psi bar psi. So I'm now working in n equals 2, so these are now complex fermions, and the i's denote they count the black holes, black hole 1, 2, etc. Now, at this layer, when you go to spin squared, for the first time, you see a description, a difference in this description of a Kerr black hole and a neutron star, and that is this, this red term here, which comes with a free Wilson coefficient, CE, which distinguishes a neutron star from a Kerr black hole. A black hole has CE is equal to 0, and a neutron star has some value of CE, which will be one of the things we would like to measure. Of course, you can now feed in this description in the same logic of this background field expansion. So for the spin degrees of freedom, we have a constant piece, which a constant psi, and then a fluctuating one, which we want to integrate out, which now has a linear propagator on the world line. And the background blue psi encodes the initial spins of the two objects. And now we can also compute the spin kick, namely the change of the spin after the scattering process. Then tidal interactions would be the next layer. So I just flash them here. You get two Wilson coefficients which couple to the electric and magnetic curvature in that sense. And again, these are intrinsic quantities describing the neutron stars. So I talked about the propagators. Let's have a look at the vertices. First of all, it's important to note that we have a sort of hybrid QFT here, because we have all the world line degrees of freedom which live on this one-dimensional world line, and we have the four-dimensional bulk theory. So we will have vertices which just live on the world line, and we will have vertices which live in the bulk. The vertices in the bulk are the standard perturbative corner gravity vertices. The vertices on the world line have a lot more structure, and they actually, at least if we start including spin, can couple an arbitrary number of gravitons to the world line and an arbitrary number of world line fluctuations, which can be both Z and psi, so you can actually compactly pack them into one superfield in order to describe it. So the coupling is, scales with square root of g to the number of gravitons. And importantly, that's, I think, the most important thing I want to convey here on this formula is that you only have energy conservation on the world line. So just a one-dimensional delta function opposed to, of course, a four-dimensional delta function in the bulk. And that fact leads to the situation that although I only want to compute tree-level amplitudes in this theory, I still have non-trivial momentum integrals to perform. So loop-like and momental integrals, just because I do not have full momentum conservation on the world line vertices. So the sort of free spatial degrees of freedom of the momenta on the vertices are still to be integrated over. That is why at higher and higher orders in the post-Minkowskian expansion, you encounter more and more complicated loop integrals, which are of a very similar type to the ones you encounter, say, in the standard model or QCD. Right. So for the bulk, as I said, it's what we know and love, higher and higher orders in the gravitons. There was a talk yesterday by Michael Ruf, I don't know if you've seen the audience, and he said this is not tractable. I would strongly disagree. This is absolutely tractable at a given order in the PM expansion. This is manageable, and of course you need computer algebra systems to deal with it. Good, so let's look at the observables that we can compute in WQFT. The first one I want to focus on, and that's where most of the work has gone in the community, is the impulse of a change of momentum of that scattering process. And translating this to the world-like QFT language, what we want to compute is the one-point function of x dot, the difference at tau is equal to infinity and minus infinity. You can, of course, write it as an integral over the acceleration. And after Fourier transform, you realize what you want to compute is just set of omega in Fourier space, in energy space, in the limit that omega goes to 0, and you sort of cut off the final propagator. So diagrammatically, what we want to compute are all these diagrams with one outgoing world line fluctuation line with 0 energy. And in these diagrams, the dots always denote sort of a background, so black hole 1 and black hole 2. And I have to sum all possible diagrams that contribute at a given order in G. So at linear order, it's very simple. We just have a single graviton exchange. At 2 p.m. order, we have these graphs. At 3 p.m. order, we have already more. And state of the art is G to the 4. For the emitted waveform, that was the little movie I showed you in the beginning, the leading order contributions, I mean, here you just need to compute all diagrams with an outgoing graviton line. I'm missing an equal sign here. This is the first contribution, and that was these three innocent-looking diagrams were the basis for this little movie I showed you, which give you that at leading order in the D expansion. I should say that this computation without spin was first performed in the 1970s by Thorn and others, but you know, in three very long papers. In our approach, it's a rather streamlined and short computation, and we were also able to update it to spin, which hadn't been computed before. And then in principle, you can also find the full trajectory, but as I said, you might not really be interested in that. So how do these computations look? So they become at higher and higher orders in the PM expansion, of course, more and more challenging, in particular from the side of generating the integrand, but even much more in the challenge of performing these loop integrals. And this is really where the you know, the Feynman integral revolution that happened in the last decade or so in quantum field theory really can be brought to use in order to access this problem. So here's sort of the workflow of such a high order PM computation. So the first step is that we need to generate the graphs. We have the Feynman rules, and this we do with a sort of recursive Baron-Schiele type approach, because we're just looking at tree-level diagrams. So that's not too hard. Then we insert the Feynman rules, and then extract the tensor integrals we have to do. Was there a question? Oh, sorry. Right. Which need to be tensor reduced to scalar integrals. And after that process, I can just give you a glimpse on what the structure of these integrals is we have to perform. So if we're interested in the n PM order, we're looking at single scale n-1 loop integrals. So at 4 PM order, which is the domain we just reached, we're looking at 3 loop integrals. And they have a peculiar structure that there's just one-dimensional quantity appearing in them, which is Q, the momentum transfer, which you can scale out. So that's this outside Fourier transform you have to do. And then you have these n-1 loop integrals, both over graviton propagators and worldline propagators, so sort of linear and quadratic propagators, and a bunch of delta functions, which tells you sort of in what mass sectors you are in. The important thing is that the blue integral that remains depends on a single parameter, gamma. This is the relativistic gamma factor in this scattering process, and that is very helpful in order to then solve these integrals systematically with the so-called differential equation method. So at 1 PM order, the single graviton exchange, the problem is trivial. We just have a pure Fourier transform, and you get sort of this scaling in the masses Ng. At 2 PM order, you have a one-loop integral to perform, and you have this mass sector and the mirrored one. And as a matter of fact, also these two contributions are completely captured just by the solution of a geodesic equation. So all terms which go linear in M1, say, and arbitrary powers in M2 can be deduced from the solution of a geodesic equation. So new challenges arise at 3 PM, at 4 PM, where you go beyond that. But I didn't want to show you these integrals here. So right. So once you have reduced to these scalar integrals, you have to find a set of master integrals, a basis of master integrals for the techniques of so-called integration by parts, which have to be updated to the retarded problem we're looking at, because they were, of course, developed in particle physics or in collider physics for Feynman propagators. Once you have these master integrals, you solve them by the method of differential equations, which essentially uses a differential equation in the single parameter these masters depend on, and then after you have to still fix the boundary conditions in these differential equations by using the method of regions, which separates then the virtual gravitons into potential and radiation modes. And then finally you find the results of your computation. So let me just show you one of these results for the impulse at 3 PM order. So the change of momentum is entirely parameterized by the scattering angle theta. It has a certain dependence on the velocities and on the impact parameter b. B is the difference of b1 and b2. And the scattering angle here, I'm showing you the results up to 3 p.m. order, has, starting at 3 p.m., a radiation reaction piece where really the difference between using Feynman propagators or retarded propagators comes into effect, and the conservative piece which sits here. This is dissipative because you can now add delta P1 and delta P2, and you'll see that exactly this contribution here is the source of a non-momentum conservation for these two bodies. That means that the gravitational waves have emitted for momentum, which you can compute for at this 3 p.m. order. And recently we updated this to the 4 p.m. Problem. So now we have we're facing 3 loop integrals, 2 integral families, certain number of masters that we have 4 sectors which we had to solve, and then you end up in quite a nice function space in which the result is then expressed after going through these steps, which now next to logarithms, dilogarithms, also feature elliptic functions in the answer. But everything just depends on gamma. So this would be here in a snapshot at the spin contribution to the 4 p.m., the spin orbit contribution to the 4 p.m. scattering angle. Here this functions f are these function bases that I talked about before. The s plus minuses are the couplings of the spin to the angular momentum. So these are the spin orbit terms. And then there's a total number of 32 of these polynomials in gamma which appear in the answer. And the thing I separated out here is the test body or the geodesic motion piece, which you get just by elementary looking at the geodesic motion in the Kerr black hole background. And that, as I said, is now state of the art. In doing these computations, as a matter of fact, you need a lot of computer power. So that was also something new for me and a lot of fun. So for example, for the problem we just faced, we had the number of diagrams were of order 200 in the non-spinning and 530 in the linear and spin case, resulting in some 10,000 integrals you had to reduce. But you could do that by then projecting them on these number of 23, 64, 66 master integrals, and then you can complete the computation. All this is analytic using Mathematica form and other techniques. So I think I have like 5 minutes. Good. So then I can also say some words now about the waveform, the far field waveform. Just let me just talk about the leading order computation here. As I said, this would be the sum of these 3 diagrams which you have to perform. Now the integrals are more tricky. They depend on 2 parameters. That's why going to so high orders is more challenging here. Of course, also here, the motivation for doing that is a little bit less, because so far we have not observed the scattering events for the, for the waveform emission. However, in this, from the scattering angle, for example, you can deduce effective Hamiltonians that also describe the bound state problem at high PM orders. Good. So the technology is now such that I can extract the waveform by looking at this one-point function of h and doing sort of an energy transform, projecting it on the 2 polarizations I have for gravitational waves, the plus and the cross polarization, and then you find the explicit waveform for the result. And this was the movie I think I showed you in the beginning. So this is now the plus polarization at v is equal to 0.4 and a certain value of b, which I don't remember. This is the plot I showed you before, or the movie I showed you before. There's a very nice effect that you can also compute here. That's the wave memory, the memory effect, because the very surprising thing about GR is that if you have such a gravitational wave passing through at infinity, that if you have a flat metric at infinity, and then the wave comes through, of course it wiggles, but it doesn't settle down to the old state. But there's a memory effect, so there's a shift afterwards. And here I'm showing you now. I mean, this is really the wave memory after the gravitational wave has passed through. you saw on the left-hand side the situation. You know, I'm looking at the celestial sphere angles theta and phi, and now this is the other guy. So it comes through and settles, and then remains like that in this nice wave pattern. Okay, this is now a movie which shows you the curvature, which of course vanishes when after the wave's gone through. So the curvature comes and then goes. All right, that was what I wanted to tell you. Of course, you know, this is such an important field that there are many groups working on that, on this, also using different approaches. And I do want to also give credit to these other approaches. So very closely related to our approach is the worldline effective field theory approach, in particular pushed to very high orders by the group around Rafael Porto at DAISY. The distinction there is that they do not quantize the worldline degrees of freedom. They only integrate out the gravitons in their approach. But they were first to reach the 4 p.m. level, which we now also managed to, and we just finished the spin orbit computation like a few weeks ago at these high orders. Then there's a very large community using scattering amplitudes as the tool to address the problem. So in a sense, there you take, if you look at this at the spinless case, massive scalar fields, quantum fields, as avatars of these black holes, and extract the classical limit from these amplitudes. Of course, from the purely amplitude point of view, there are even more developed or more efficient techniques to compute these objects than in our worldline theory. However, there the challenge lies in extracting the classical limit, which becomes a lot more complicated than in our formulation, where we just have to look at the tree-level diagrams. And then there's sort of a hybrid thing known as heavy black hole effective theory, which is related to the heavy quark effective theory approaches known in particle physics. And here on the waveform side, the amplitudes and heft community has just recently updated the result I showed you to the next order, yet for spin it has not yet happened. Okay, this was and then I should also, I'm sorry, just 2 days ago when I was preparing these slides, the group of Van Hove and Damgaard and Plante published the first amplitudes-based computation of 4 p.m., including radiation reaction. So that's when and we all agree. So that is also, of course, very important that you have different techniques which are, brought to, which are performed independently of each other in order to be sure that one really has the correct results. Good. So that was what I wanted to tell you. My summary is, I hope to have given you a glimpse of worldline quantum field theory as a highly efficient quantum field theory-based technique to compute classical gravitational wave physics in ordinary GR. The methodology was that we quantize the worldline degrees of freedom. We have to compute only one-point functions at tree level, which directly lead us to the observables. We have to use the in or Schwinger-Keldysh formalism, and we can include the spin degrees of freedom, I think, quite elegantly through a worldline supersymmetry, which is also the reason why sort of our group is ahead in the spin interactions. Open problems, the next order. First of all, we need spin squared at 4 p.m. We also wanted to reach 5 p.m. in order to reach the accuracy that is needed for the next generation of gravitational wave detectors. The formalism, the supersymmetric formalism that I introduced you to right now hits a wall at n equals to 2, and we have to see how we can go to higher spin descriptions with SUSY here. That's an open problem. Of course, we want to make progress in more on the bound orbit situation, and potentially also make contact with the so-called self-force expansion, which is an expansion not in G, but in the mass ratio. Thanks for your attention.
Okay, let's take a few questions.
Thank you. Let's see if there are questions from audience here.
So let's first there and then. Yeah.
They're already asking.
They're already asking. Okay.
Okay.
Thanks. I have two questions. To what extent has there been a comparison with numerical GR calculations? And the second question was, Is there any estimate on the rate that we can expect these things to occur in the universe, these scattering phenomena?
Yeah. So to your first question, sort of the benchmark for us are numerical relativity computations. I can show you one plot which sort of resolves that. Well, first of all, for the numerical relativity, the in-spiral phase is very costly, and the reason why you need analytical results is because we need to set up these huge databases of waveforms, with all various different parameters for the data analysis. Now, filling these tables with pure NR computations is just way too time costly. In particular, also a long in-spiral phase. I mean, it's very good in the merger phase when the perturbative description breaks down, but in the in-spiral phase, it is much more efficient to use our analytical results. Then, what I've been talking about scattering is just starting to be looked at from the numerical relativity side. So what I have here is a plot where we did some sort of a matching procedure where we used the scattering data, the conservative scattering data, to infer an effective Hamiltonian, including spin, which you can then use for a bound state problem in which numerical relativity data exists. And here you can see, this dotted line here would be for a particular spin configuration and masses. This is the NR computation, and you can see when you go up to 4 p.m., now we don't have the linear spin results in yet, you get better and better in terms of that. So that's I didn't pay the right attention to NR. It's very important. It's sort of, I think in this science, you want from all sides, you want to just combine information from all sides. Then from the second question, this is a very astrophysics question, so I'm not really the right person to ask, but for these scattering events, for example, there is a chance that it might be detectable at LISA because it goes to lower frequencies, and that depends a lot on the sort of astrophysical scenarios, how often such scattering events happen. But I should
Let's
speed up by
take one
looking
quick
at
question.
Ilma, one thing, we will need to start sharp again at 11 because we have something after this session. So just want to warn you.
Jan had a question, but I don't know if that's
Yeah,
allowed.
but not more, I think.
Yeah, so you have partly answered it right now, but I was just going to ask how large energy is involved in this scattering in the radiation. I mean, we know with the binaries, it's several solar masses.
So how
large
much?
is
I can't give you a precise number now. No, not out of the top of my head. Yeah.
So I'm afraid we are short of time now.
I mean, we have P naught. I could just look at it and divide it by the total, but I don't know. I have never done this computation, how much percent it is. But it's a good question.
So we are short of time now, so let us break now. Sorry, what? So is there any questions from the other side? Sorry about that.
It seems no, and we should start sharp at 11 because we cannot go over time with the next session. So maybe to break now and reconvene at 11 sharp.
Okay, then we start again here at 11, so short coffee break.
Okay. Okay. Before you
I will go there. I will go there. I will go there. You ready? Okay. Good. So please hurry up and take your chairs. We should start on time. And please move in the middle as far as possible. Okay, so let us begin. So it's a real pleasure to welcome Professor Christoph Wetterich from Heidelberg for this talk. He has made many contributions over the last several decades to cosmology, particle physics, and so on. And today he will talk about quantum gravity predictions for particle physics and cosmology.
Thank you. Thanks also for this nice meeting here and invite me. Quantum gravity predictions for particle physics and cosmology. Perhaps I should first say a few words about what I understand by quantum gravity and what aspects of quantum gravity I really want to talk about. Well, first of all, quantum gravity, for me, the most important thing, that's about the fluctuations of the gravitational degrees of freedom. It's the fluctuations of the metric or the Vierbein or whatever you want. We should not forget, when we speak about the difference between a classical field theory and a quantum theory, that's the main difference. The difference between classical electrodynamics and quantum electrodynamics, that's that we talk about the fluctuations of electrons and photons, and that we get then effective equations of motion, effective Maxwell equations or their modifications by having a functional integral for quantum electrodynamics. So if you speak about quantum gravity, my own judgment to which extent you are quantum is, can you really deal with the fluctuations of the gravitational degrees of freedom of the gravitational fields? So that's for me the main question. And you know, when you judge certain pretensions on quantum gravity, you sometimes think, if you ask them, I have a big effect of quantum fluctuations, for example, for scalar potentials, have you any chance of computing that? For example, I ask my string colleagues, then often I get, it's very hard, fluctuations to compute that string field theory, we do not really know. And I think I say it for purpose, not for criticism, but if you really want to say something about quantum, you have to speak about fluctuations. Now, I'm specific. Today I will speak about the importance of fluctuations close to the Planck scale, or above the Planck scale, shorter distances. There's a very well-developed methodology for computing metric fluctuations in effective field theory for length scales much larger than the Planck length. That's John Donoghue and a lot of people. Very nice work, but the effects are small, very small. Here we are really talking about the effects of quantum fluctuations of the metric around the Planck scale and above the Planck scale. So of course, very often it's not necessarily the metric, it can be the Vierbein, it can be the spin connection. How you set up your field theory exactly, that's secondary. You have additional fields, fermions, scalars, and so on. But the important thing, it's field theory. You have fluctuating fields. That's key. Now, some of you say, well, after all, that may be not so relevant because we expect anyhow a completely new structure of quantum, of a theory with completely new entities. The metric is only a composite field, and the new theory has has to be formulated conceptually completely differently. It's not that I'm not a friend of it. It's actually my own view. I personally think that the metric is actually a composite field of something more fundamental. Everybody has its own favorite theory. Mine is lattice spinor gravity, only fermions on the lattice with diffeomorphism symmetry. That's all nice, but you have to answer the question, at what scale will that be important? Is it really at the Planck scale, or is it at a scale much, much shorter than the Planck length? And this is not a completely harmless question, because it's often overlooked that we actually have traces of such a completely different theory, possible traces, in the cosmic microwave background and through the primordial cosmic fluctuations. I recall you that inflation really acts as an enormous magnifying glass. And the fluctuations that we observe in, let's say, the distribution of the CMB, they, at the time when they left the horizon, they have been larger by about 20 E-foldings, typically larger than the Planck scale. So, of course, when they leave the horizon, there are fluctuations where classical gravity should be very, very relevant. But it's just 20 E-foldings. And inflation typically lasts 60, 70 E-foldings. So at the beginning of inflation, these same fluctuations have been much, much smaller. Their wavelengths have been much, much smaller than the Planck length. So whenever you do something very complicated and very drastic, be warned. You cannot necessarily hide everything. For example, you have to produce a high degree of isotropy and things like that. And it's not that you can be completely hidden from observation. Whenever you say my theory has also an inflationary phase and it covers the early parts of the inflationary phase, then you must be sure that at the end your fluctuations are those that are described by a nice field theory, continuous fields, and so on. So for that reason, it's one of the main reasons I actually think we really should understand what happens with fluctuations at the Planck scale and much shorter than the Planck scale, because most likely, even if you have a completely different effective theory with composite degrees of freedom, it needs a field theory description for many, many orders of magnitudes above the Planck scale in energy, up to the Planck scale, and then, of course, up to now. So that's the general setting. Let me just resume. Quantum field theory is a field theory. It has a metric field. And actually, that's a key thing. The metric is a field. It can be actually a composite field, as we have it when we have laboratory quantum gravity. People just mimic some hydrodynamic equation that have the same type of tensor field as the metric. That's very nice. It's not complete, but it's very nice. But you need a metric field, and actually that was my remark yesterday at this public lecture. We should be a bit more modest when we think, we really observe how matter changed the fabric of space-time, or how the vacuum is completely different. It's much simpler. The only thing that changes is actually a field. When we speak about an expanding universe, the only thing that changes is the value of the metric field. That goes from, let's say, even 0 at the Big Bang to some finite value. It's a field change. And I recall you that in quantum field theory, the field the choice of fields is not unique. You go to a different metric frame by so-called Weil scaling, you get a completely different geometry. So I think it's a bit misleading when we always say, we deform space and so on. That's an absolutist way of geometry, and geometry is not so absolute. Geometry is given by a field, and we can choose different fields in order to describe it. At the end, that will even be a little bit important for my talk. So what these people with laboratory general relativity cannot do is another important ingredient, that's diffeomorphism symmetry. That's a basic fact. Gravity is a gauge theory. It's a gauge theory just as quantum electrodynamics. The gauge symmetry is general coordinate transformations or diffeomorphisms. So that gives me the setting. If I want to speak about fluctuations, I should set up a functional integral as I do it for QED. And this functional integral should be invariant under diffeomorphism transformation as a gauge symmetry. So that's the basic setting. And it's inside this setting I want now to describe the role of quantum fluctuations of the metric or the Vierbein, and the role it has for predictions both for particle physics and cosmology. So I hope the overall setting is clear. Well, there's of course also a few differences to quantum electrodynamics. So in a certain sense, it's similar to other quantum field theories. You would say the metric is a tensor, photons are and gluons are vectors. That's actually a minor difference. You can even formulate quantum gravity, of course, in terms of Vierbeins and spin connections. These are vectors, so that's not a big deal. So a more important issue is that quantum gravity, Einstein gravity, is not perturbatively renormalizable. I mean, that is the point that has scared people for a long, long time. People have said, okay, we cannot just use quantum field theory, standard quantum field theory methods, because if we compute perturbation theory, everything is diverging and you cannot renormalize. There is no small intrinsic dimensionless coupling. There's an effective coupling, which is energy squared over the Planck mass squared or momentum squared over the Planck mass squared. So that's why quantum effects are very, very weak when we go to TeV energies. But that's also when we go with Q squared above the Planck scale, where typically diagrams diverge and you get into a problem. Well, true, that's an issue. It's not perturbatively renormalizable, but it's non-perturbatively renormalizable. I mean, this is this old idea of asymptotic safety, pioneered by Steve Weinberg, and then I think for pushing it to a practical work in 4 dimensions, that's Martin Reuter's merit to have gone this step. And of course, you need a method to deal with it. You need a non-perturbative method, and the method of my choice, you may not be surprised, is functional renormalization, because that really gives you finite answers how to compute in a gauge invariant way the effect of quantum fluctuations of the metric. Renormalizability from this point of view is a very simple fact. It's the existence of an ultraviolet fixed point. That's all. If you have an ultraviolet fixed point, then you can extrapolate your theory to infinitely short distances. Let me be a little bit more precise. So what you look at, you look at the change of couplings with some renormalization scale k. And this renormalization scale k, that cuts off all fluctuations with momenta smaller than k. So it's just a technical thing. You look at your quantum field theory, has fluctuations on all scales, on all momentum scales. You have an infrared cutoff. You cut off first the fluctuations with momenta smaller than k, so you have included everything all momenta bigger than k, and then at the end you lower k to 0. And then of course if you change k, the couplings depend on k of an effective theory, not only coupling, whole coupling functions, that's why it's called functional renormalization. And at the end you go to k to 0, and all functions are included in the infrared limit. On the other side, if you go with k to infinity, you have the ultraviolet limit, and if there is a fixed point, then nothing changes anymore. A little warning, the scale k is not necessarily identical with an effective momentum scale of some scattering amplitudes or with some curvature in geometry. People often take this shortcut, but it's pretty dangerous actually. If you have only one single scale, only logarithms, like let's say the running of alpha in QED, then this identification works very well. For more complicated problems, there's a clear procedure how you should do it. I will not discuss it, that's much too technical, but just a warning, it's not identical. Now, ultraviolet fixed point simply tells you that the dimensionless couplings do not change anymore when you go with k to infinity. And then, of course, the theory is complete. There's nothing missing. You can go to arbitrarily short distances or arbitrarily large momenta, and this is what is called a renormalizable theory. All renormalizable theories are actually of this particular type. They need to have an ultraviolet fixed point. Lattice gauge theory people also know that very well. And then you have completeness, and everything you could, in principle, you could live with this theory. Doesn't have to be, when I say that quantum gravity is a renormalizable theory, a non-perturbatively renormalizable theory. This does not mean that it cannot be something more complicated. It's just that there is a possibility that a field theory description is enough. That's already an important insight. And of course, it tells you that if you have something more profound where the metric is composite, and this is valid for many, many orders of magnitude, then this renormalizability of the theory of a metric is, of course, a very important tool because it permits you to bridge from your microscopic scale to the Planck scale and beyond. Asymptotic safety in the particle physics community, it's often considered as something a bit strange. It's, in the principle, very simple. It just tells you that your ultraviolet fixed point, the couplings do not vanish. That's asymptotic freedom. Gauge theories, couplings vanish at the ultraviolet fixed point. Asymptotic safety, the couplings do not vanish at the ultraviolet fixed point, and that's the basic reason why you cannot use simple perturbation theory. So particle physics now slowly changes its view, but if I ask the same question to a solid state physics guy, he would say, what the hell, what are you speaking about? That's trivial. Our fixed points are of this type. If you look, for example, at the Ising model or its continuum version, there's the Wilson-Fisher fixed point. This is a renormalizable theory. In principle, you could go with this continuous and O2 model to infinitely short distances. That's not interesting for solid-state physicists because they have a lattice, they have atoms, and so on. But of course, from the theoretical point of view, these are perfectly renormalizable theory, and even the simplest fixed points that we know, Wilson-Fisher fixed point and so on, they are perfectly of this type. These are asymptotically safe theories. There are many fermionic asymptotically safe theories, and so on. I think nowadays, this should not be a question of principle, but just be a question of practical implementation. Is there such a fixed point, or is there no fixed point? And if there is a fixed point, and it's at non-zero coupling, it's as good as a fixed point as zero coupling. So, asymptotically safe gravity says simply this ultraviolet fixed point exists in a quantum field theory for the metric or for some other fields, and now I come to predictions of it. And I first start with predictions for particle physics. Can you do predictions from this very simple setting, functional integral for the metric? You understand the flow of couplings, you have a fixed point. Can you get predictions for particle physics? Well, the answer is yes. And the best example is there has been one. There has been one on the mass of the Higgs boson. That was 126 GeV with a few GeV uncertainty. And the interesting thing is perhaps the date. This was not a post-diction. It was a prediction. And I think it's still a prediction, and the assumptions and the uncertainties that have been around at this time in 2010 have been to a large extent clarified by now. It still remains a prediction of this access, of this simple feature that there's a quantum field theory, renormalizable field theory for quantum gravity that is beyond at least a few orders of momentum larger than the Planck scale. That's all you need. You need just, if you have, let's say, 5, 6 orders above the Planck scale, that's enough to make this prediction. So I want to explain you a little bit how such a prediction comes about. Not, first of all, because it's a nice prediction, but because it's also the simplest one in a certain sense. There have been many other predictions that I will only touch briefly, but you should understand the basic principles, how you get to such a prediction. So why can quantum gravity make predictions for particle physics at all? Naively, you would say particle physics, that's TeV at best right now, and TeV over M Planck, that's 10 to the power minus 15 or so. You square it, forget it. And of course, it's not the graviton fluctuations at TeV scale that really matter. We will have to go to a regime where the gravity fluctuations really are important, and that's typically Planck scale. So how is the relation? It's not so complicated. If you want to make a prediction on the Higgs boson mass, since the Fermi scale is known, you need a prediction on the value of the quartic scalar coupling lambda, because the squared Higgs mass is just proportional to this quartic scalar coupling. So if you can predict this quartic scalar coupling, you can predict the Higgs boson mass. Now, of course, if all couplings, QCD couplings or QKV couplings, also the quartic scalar coupling runs, and actually if you follow the experimentally measured value to larger and larger momenta, you come very close to 0, which is already a quite important observation that's actually going under the name of vacuum stability and so on in the particle physics community. So once you see this diagram, well, you see, well, now I'm in business if I can make a prediction about the initial value of this flow around the Planck scale. The prediction actually of quantum gravity is this value is very, very close to 0. So if you make this prediction at the Planck scale, then you extrapolate to the Fermi scale and you get what is the observed value of the Higgs boson mass. Little warning, you have to go from here to here. So this figure here would have the great desert. Nothing happens. So we make a prediction at the value of the quartic scalar coupling at 10 to the 18 GeV, and then you say, I can now safely extrapolate with the standard model perturbative equations until I come to the Fermi scale. Well, a great desert is, of course, not so nice. That's no supersymmetry, no low scale dimensions. I've shown this diagram quite often. I know it's a bit provocative. This is, of course, a nightmare for some of my experimental friends. But you should not forget, for a theorist, such a situation would be the most beautiful that we can hope. Because if there's plenty of stuff in between, you have not much chances of really connecting Planck scale physics to observation. If there is nothing, then of course we know in QED we can, for example, for many, many orders of magnitude, QED is valid. We can really connect phenomena at very different distance scale. And if you want to have a possible look on experimental look on quantum gravity, that's the best situation that could happen for us. There's nothing in between. It's a bit radical. Actually, there may be some oases in the desert, and there are certainly some oases. You need some for dark matter, mass generation for neutrinos, axions perhaps, some other beyond standard model particles. But what remains true, the effect on the running of couplings like the quartic scalar coupling should be small. If you have something like supersymmetry, low energy supersymmetry, that would completely change this prediction. One should not forget that. If you have only an additional right-handed neutrino or something like that, that is a typically small effect that accounts about in this few GeV uncertainty that I was telling you. But if there is much stuff in between, forget it. And then you can forget this particle physics part of my talk, and you can come back with cosmology. But let's assume that actually not so much happens in between. Then I can really explain you how this prediction comes about, and this will also give you a feeling, a quantitative feeling, how you can understand these things. So near the Planck scale, gravity has predictive power because the effect of graviton fluctuations is a large effect. So that's the important message. And let's just go directly to the running of the scalar coupling. And for the moment, forget all other fields and just look at the contribution of the graviton to the logarithmic running of this quartic coupling with the renormalization scale k. That's given by some anomalous dimension times lambda. So that's already an important fact. It comes simply because the diagram is you just attach a graviton loop to, in this case, the propagator, but you can, of course, also have higher legs here. So the general structure of the gravitational contribution is an anomalous dimension. That tells you it's already, if you go to small lambda, it becomes quickly the biggest effect, because the pure scalar loops will be lambda squared and so on and so forth. So, and in addition, you typically find this anomalous dimension is not really small, it's sizable. It's 0.1, it can be even 1, could even be bigger. It's an order 1 effect. So that's two important things. And this A is positive. That was not yet completely clear at the time of the prediction, but that's very well settled by now that this A is positive. Now, in the limit where this A is constant, it's of course a differential equation I could even solve at the blackboard. The solution is lambda of k goes with lambda of some mu, where I've put initial values of the flow, times k over mu to the power a. And of course, if k goes to 0, lambda goes to 0. Or you can read this formula in a different way. Let's say I want to know the value of lambda at the Planck scale. Now I want to have the validity of my theory at least up to a scale mu. That's perhaps where your favorite fundamental different degrees of freedom set in. Let's say this is a question which is at most 10 or 100 or 1000. But then you have a big factor k over mu to the a that reduces it to 0. And that's, one of the simple things that when you have such a type of fixed point, which is called an infrared fixed point at lambda equals to 0, you see the quartic coupling flows towards this fixed point when k is lowered. That's called, and couplings with this type of behavior, they are called irrelevant couplings in the language of renormalization theory. Irrelevant couplings mean simply they can be predicted, because the theory says that if you extrapolate your theory to infinitely short distances, if you really approach the fixed point more and more, then you have a firm prediction this lambda is 0. So that's a so-called irrelevant coupling, and these irrelevant couplings give you predictions. And here you see already the basic principle how quantum gravity can give you predictions on standard model or beyond standard model couplings, namely whenever such a coupling corresponds to an irrelevant parameter, that it can be predicted. There are also relevant parameters. They cannot be predicted. I will come to one of them today. So that's the key of the prediction. The quartic scalar coupling is actually an irrelevant parameter at the ultraviolet fixed point, and then it can be predicted. And the value of the coupling, it's not precisely zero. It's actually very, very small because you also have effects of gauge bosons and so on. Forget that for the moment, for all practical purposes. It's just zero. Nowadays, at the beginning, you know, these were very complicated equations. Nowadays, I think we have a pretty good understanding. We can even give closed formula for this anomalous dimension. Here you see, for example, the traceless tensor contribution, which dominates in this case. V0 is something like the cosmological constant, dimensionless. You do not really need its value. What you need to see is this 1 over mp tilde squared. What is that? That's the strength of the gravitational coupling. mp tilde squared is simply the Planck mass squared divided by k squared in order to make it dimensionless. But the m squared, the mp squared, is again a running coupling. It is not just the constant Planck mass here, but it has another contribution when you go to very, very high k. It is given by a fixed point, which is mp tilde star squared times k squared. And now you see that when you go with k squared much bigger than m squared, so if you go really beyond the Planck mass, then this 1 over mp tilde squared just goes to a constant. And we are really at this observation, at this situation where we have a constant gravity-induced anomalous dimension for the quartic scalar coupling. So it's as simple as that. You need a running of the Planck mass. You also see that when mp tilde squared becomes larger than 1, so when k goes below the Planck scale, then these quantum gravity effects essentially decouple, and only the standard running of the quartic scalar coupling remains. But above the Planck scale, they are actually the dominant contributions. So that's now already the basic picture of how asymptotic safety works. Because you have this effective gravitational coupling strength, so this 1 over mp tilde squared over k squared over m squared. That's a very small quantity when you go to GV or TeV, because it's suppressed by many orders of magnitude. Then if you go with k to larger and larger scales, the quantum gravity effects become more and more important. And then instead of diverging, the fixed point in the running of the gravitational constant tells you this will go to a constant, this will approach this ultraviolet fixed point, and that's why you have a renormalizable theory of quantum gravity. Again, I should give you a little equation for the running of the Planck mass. Because again, it's a very simple equation. It's not complicated. Actually, the scale dependence, the logarithmic dependence of the Planck mass squared is just proportional to k squared. That's the only scale that it's in the game. There are no mass particles. Everything is massless. That's what you expect. It's not surprising. It's really the simplest thing that you have. Don't think that asymptotic safety is something complicated. It's just the simplest possible behavior that you have that gives you the answer. Actually, it's not only the graviton contributions that contribute to this C. There are, of course, matter contributions. For example, there is this NM. That's 4 times the number of vector fields, gauge bosons, minus the number of scalar fields, minus the number of Weil fermions. This particular combination is pretty old. You find it in old work on induced gravity by Adler and so on and so forth. It's just loops of fermions where you attach gravitational fields to the outside. The only difference is before these were coefficients of divergent diagrams, and people didn't really know what to do, so they put some artificial ultraviolet cutoff which would violate diffeomorphism symmetry and so on. By now, with functional renormalization, you have the same type of loops contributing, but everything is finite, ultraviolet and infrared finite. The change with scale only, of course, involves the scales, the momenta around this scale, and that's why everything gets finite. So that's a matter contribution. In addition, you have a contribution from the graviton fluctuations. That does not change the whole thing qualitatively. Quantitatively, it matters, of course. So the message I want to say is asymptotic safety is a simple setting. It's the most natural setting, but it has, of course, still the gravitational coupling, which is non-zero. It's not a free theory. Gravity is never a free theory. Never was wrong, but in general, it's not a free theory. And you have a fixed point value for the dimensionless Planck mass. And then I told you already from there, you once you have, of course, this type of flow equation, you can again very simply solve it. That's the general solution. You have a free integration constant. That's the observed Planck mass. And you see that's now an example for a so-called relevant coupling, because the Planck mass today is not a predicted quantity. You see if you have a free integration constant in this solution, this m squared, and for different settings of m squared at some short distance scale, you have different solution of the flow equations, and you have to fix on which trajectory you live in order to have the Planck mass that you observe. So it gives you this picture, but now you have an example of a relevant coupling. These few remarks already tell you the general story how you get predictions. So free parameters of a theory, they correspond to relevant couplings. You cannot predict them. But if you have less relevant parameters at the ultraviolet fixed point than the total numbers of renormalizable couplings in the standard model or in some beyond standard model theory, then you get immediately predictions about relations of standard model parameters, and that's the Higgs mass was one example. There are by now many other examples. The standard model, first of all, which is important, can be reached from such an ultraviolet fixed point. That's highly non-trivial. It could also, the answer could also be that we make predictions that contradict what we observe in the standard model. This has not happened. It's a very non-trivial statement. And then, of course, you can also go beyond the standard model. There's a whole standard model landscape, beyond standard model landscape. Not everything goes. I thought I spent more time on it, but since I'm already a little bit late, let me just say that once you have understood the basic principle, you immediately realize now that for many extended theories, you get also predictive power, and not everything goes. So that's the important message. You cannot do any more what you want. If you really say, I want to embed that in a theory of quantum gravity, where the metric fluctuations, at least for a certain range beyond the Planck scale, can be dealt as a field theory, then you have to live with the predictions of this theory, and they very often tell you, well, no, it's a nice model, but it's not compatible with this simple idea of quantum gravity. So that's my first conclusion. Quantum gravity is a renormalizable quantum field theory for the metric or for the Vierbein. It's realized by an ultraviolet fixed point, which is typically non-perturbative, and it's predictive. Mass of the Higgs bosons, there have been constraints on the mass of the top quark, scalar potential in grand unified theories. That's a very important issue for those people interested there, because this was the big uncertainty when I was young and I was doing gut theories. You had all these scalar potentials and you could arrange for everything what you wanted. Now you predict that all these quartic scalar couplings are zero, because it's not only the Higgs boson couplings, it's all quartic scalar couplings that have the same status. And then you have to live with it, that now all of a sudden grand unified theories become very restrictive anymore. And then restrictions for beyond the standard model particles. Let me come to cosmology. Let's try to be a bit briefer. Well, the simplest way how you, let me start differently. So far, we were only speaking about standard model without gravity. But of course, we also have a lot of information on standard model coupled to classical gravity. And I think we definitely need some type of inflationary scenario or some similar scenario in order to have a reasonable theory of our universe. And so for me, one more criterion, if the standard model coupled to gravity can be formulated as a quantum field theory in this way, is that it should describe inflation. There's one simple solution to it. That's simple, that's the coefficient of the term proportional in the curvature scalar squared alpha. This is actually a relevant parameter. So you cannot predict it, and then you can take it as large as you want. And in particular, for very large alpha, you can realize the Robinsky inflation. There is very nice work by Frank and collaborators really giving the precise trajectories, and that's definitely a possible solution. It's not the solution I like most, and I tell you a bit about the solution I like most because it's quite instructive. It goes a bit beyond the couplings of single couplings. It has more the functional side. So let me look at inflation and dynamical dark energy at the same time. So it's now quantum gravity with a scalar field and typically with a scalar singlet field. People try to have a single field both for inflation and dynamical dark energy. There's a whole list of people that's called quintessential inflation. They take up a potential which goes to a constant on one side for phi to the minus infinity, so that's inflation, and then it goes to zero, but it approaches zero only slowly, and that part gives you dynamical dark energy. Very nice figure, and of course, in principle, you can, when you are not dealing with quantum gravity, you can say, well, I just write down my potential, and I calculate what comes out with this potential. Now, quantum gravity actually tells you what is the form of such a potential. And the interesting thing is quantum gravity predicts you that this is actually the form of the scalar potential. At least a large class of quantum gravity theories will predict that. And let me go through this argument a little bit in more detail. So once you speak about the whole potential, you see it's not single couplings. It's whole functions that you have to predict. And that's actually what functional renormalization does. At the ultraviolet fixed point, it's not only a finite number of couplings that have a fixed value, it's whole functions, functions of momentum, functions of scalar fields, and so on, that go to scaling forms. So in a sense, that's infinitely many couplings that are predicted. Most of them are irrelevant. That's why you can predict these things. But it's a prediction. You predict that an ultraviolet fixed point can only exist if functions like dimensionless scalar potential as a function of the dimensionless field, if that goes to a scaling form. So scaling solutions are now very restrictive. That's something really new. And that's not so difficult to understand. These are now differential equations that link the value of the scalar potential at field value 0 to infinity. That should be a solution for the whole range. And just as in atomic physics, once you have boundary condition on both ranges, things start to be very restrictive. And actually, that is the heart of the additional predictivity of quantum gravity if you really look at whole scalar potentials. And that's important because we know we need in cosmology, we need the potentials over large ranges. We need the inflaton potential or the Higgs potential for Higgs inflation or the Cosmon potential for dynamical dark energy. And the nice thing of quantum gravity, it is predictive. These potentials are no longer arbitrary. So that's the form. Generic form of such a potential, it goes from one constant, so that's not 0, to another constant with a little tradition. So with a little transition. So what you see here on this plot is a dimensionless scalar potential. So I just divide out the scale k to the 4 in order to have the potential dimensionless. And x is the logarithm of the scalar field value. So it goes from one value for phi to 0 or chi to 0 to another value to another constant value when the scale grows large. And you immediately notice that's pretty different from the polynomial potentials that we have in, let's say, the standard model or so. This is a generic form. It goes from one constant to the other. And there's actually a simple reason for that, because a scalar potential is nothing else than a type of field-dependent cosmological constant. The cosmological constant runs with k to the 4. And so that's, again, the standard canonical running. And only the effectively massless degrees of freedom contribute. And there's simply the observation that the number of massless degrees of freedom when, let's say, the Higgs field is 0 is different from the number of massless degrees of freedom when the Higgs field goes to infinity, because then gauge boson masses and so on go to infinity. And for this reason, the potential actually makes a little shift from one constant to another constant. But if we forget about this shift, the prediction is simply the scalar potential is a constant. So let's keep in this simple form. So that's the prediction of quantum gravity, almost constant scalar potential. And there's a second function I've drawn here, that's the function W. That has to do with the strength of gravity. And what you do is you go now to second order in a derivative expansion for gravity coupled to a scalar field. You have not only the potential, you have the kinetic term, on which I will not say much, and you have the factor, the prefactor of the curvature scalar, which is again, in a type of field-dependent squared Planck mass, this f. And this function w, this is nothing else than this field-dependent Planck mass squared divided by k squared. And that has now a different form. It's not a constant. It's a constant when you go with x to the scalar field chi to 0. But then it grows like chi squared when chi goes to infinity. And it's again very simple to understand, because there's a simple renormalizable dimensionless coupling xi times chi squared times r. That's sometimes called a non-minimal coupling of a scalar field. And if this xi is different from 0, then this prefactor goes to infinity when chi goes to infinity. Again, a very simple form. That's what I have shown you here. That's the approximate scaling form, flat potential, and a non-minimal coupling of chi squared to the curvature scalar takes you this function w increasing linearly with chi squared. Looks natural, no? Looks not complicated. There's no small parameter. Everything is order 1, simple form. Nobody would complain about that. I warn you, once you swallow it, you solve a lot of things. You solve, for example, the cosmological constant problem. So if you are critical, you have to criticize this simple function, this simple form here. You can say that cannot be, or that's wrong, or that's unnatural. I don't see anything unnatural here. So let's just look what are the observational consequences of it. How to link that to this potential. Well, it's pretty simple. Since we have a theory where the Planck scale depends on the scalar field, it's pretty complicated to compute. You can compute in this version, but it's much simpler to do a so-called Weil scaling, to use a different form of the metric. You just have a new metric that is m squared over f. The old metric is m squared over f. F was this field-dependent Planck mass divided by g prime mu nu, multiplied with a new metric. And you see the Planck mass comes here in only by this field redefinition. No, it was not present before in the simple curve with u and v. It comes only in by this field redefinition. You also make a rescaling of your scalar field such that the kinetic term, a constant kinetic term k, will correspond to a constant wave function renormalization z. And then you can link this theory of variable gravity to a standard gravity with a fixed Planck mass. That's the so-called Einstein frame, and the potential. And the potential is simply the potential u multiplied by m to the 4 divided by f squared. This simply comes from the factor square root of g. It's very simple, standard Weil scaling. You do it, you have this u as some constant, f another constant, plus a term proportional to chi squared. You do the Weil scaling, that comes out. That comes out, even, you know, it gets an exponential form. It goes to exponentially to 0. And what is important? Actually, it goes to 0. There is no offset. That's the solution of the cosmological constant problem. It's as simple as that. And this, once you see it in the other frame, it's actually very simple, since u is a constant, and the only thing that you can observe is the cosmological constant divided by the 4th power of the Planck mass. And if the Planck mass increases proportional to a scalar field, and you go with a scalar field to infinity, well, the ratio goes to 0. And then you do Weil scaling, you see exactly that. So that's a very simple solution, and this is an old solution, and it's still valid. And I do not understand why people can say this is unnatural, because what you have to criticize, if you say it's unnatural, you have to criticize this simple form here. Naturalness arguments, you have to be very cautious. You really have to understand that they can depend pretty much on the frame, on the fields that you choose, and they can be pretty wrong sometimes if you have fields that are not really convenient. So you can now build, actually, when you take some assumptions for how the kinetic term, about the functional form of the kinetic term, you can even build very realistic models. So you can make predictions, but the predictions depend on this kinetical k, and this still needs to be computed in a reliable way. In my view, even so I did with collaborators some early computations. This is not yet really settled, but once you have computed this function k, you really make predictions on epsilon, eta, the amplitude of fluctuations, and most likely it will go wrong, because if you just have your first model, because quantum gravity is really predictive on that, and you cannot do whatever you want to get. I want to finish with a little remark on the Big Bang. That's why I cut this short. Conclusion of my second part is simply that quantum gravity can compute the form of scalar potentials. They are crucial for many aspects in cosmology. That makes quantum gravity really predictive, because here now there's much less room to play. We predict whole functions, and you compute what are the primordial fluctuations corresponding to it. You have to get the small amplitudes, actually good mechanisms for it, but it's highly non-trivial that once you compute this k of chi, that it really has the form that you need in order to produce the observations. And once you have computed it for a given model, you have definite predictions for this model. So let me take my last 5 minutes, not more, for the statement, what has quantum gravity in this picture to say about the beginning of the universe, the Big Bang? Well, one can just compute. What you find is a pretty boring universe. The beginning is, I sometimes say it in German because I find it in German particularly nice. Zu Anfang war die Welt öd und leer und währte ewig. You can translate it to English. The beginning universe was empty and lasted since ever. That's a statement. That's the beginning. And that's the beginning of this ultraviolet fixed point. You start arbitrarily close to the ultraviolet fixed point, and if you have an ultraviolet fixed point, you're not surprised nothing happens. Because as long as you are at a fixed point, exactly nothing happens. So actually, this beginning is just a beginning where all particles are massless. That's fluctuations dominate. Actually, the metric field even vanishes. You have exact quantum scale symmetry. That's the ultraviolet fixed point. You should not be worried about the vanishing of the metric. You can go to an equivalent metric frame, the so-called primordial flat frame, where the initial geometry is just flat Minkowski space. The geometry is not an absolute criterion. But what is important is there's only fields and fluctuations, and the time there is in the limit where you're exactly on the ultraviolet fixed point, there is no time dependence. So that's only fluctuations. Actually, fluctuations dominate, and all particles, the few particles, are relativistic, have no mass. But then, of course, this ultraviolet fixed point is actually unstable. When you have a tiny value of the scalar field, that will start to grow. It grows, and as it grows, at some moment it goes away from the fixed point, and from there the qualitative cosmology changes. You produce entropy, you produce particles, you see the fluctuations in the microwave background. Of course, the timing is very different. It's now not 13 billion years ago, it's thousands of billions years ago, depends on your precise model. But it produces you exactly the same physics here. So, seems a bit strange at the moment. You have now a completely different story of the universe. You have this great emptiness story, start with a fixed point in the primordial flat frame, even with Minkowski space. Only a scalar field is growing, and with this scalar field, all masses of particles are growing because they are proportional to this scalar field. That's a story. But then you have a completely different story, the Big Bang story, where everything started with a singularity, and you ask, come on, only one of them can be right. That's wrong. It's the same physics. It's the same physics. You can really map one of these stories to the other by a simple field transformation of the metric, and I think that should be a real lesson when I say geometry is not something absolute. The geometry is very different from this picture and from this eternal vacuum. Nevertheless, it's just the same physics, and actually, in this case, it's a singular Weyl transformation that brings you from one picture to the other, and that's where the singularity comes from. It's actually not a physical singularity. It's a so-called field singularity, not a coordinate singularity. When you go to a singular frame that produces you the Big Bang singularity, it's a singularity in field space, but there is no need to choose fields where things get singular. That's just like Antarctica, that's being singular in one map and not singular in another. And that is my conclusion of this last part. Actually, once you have an ultraviolet fixed point, you typically also have the possibility to have a universe that lasted for infinitely long in physical time. You can arbitrarily far go back, closer and closer to the fixed point. And what we call Big Bang singularity is simply a coordinate singularity in field space. That's a bit disappointing in view of all the books and essays that have been written about it. But I've said that since now many years. Nobody has come with a valid criticism about it. Of course, I had many discussions with people like Starobinsky and Linde, but I think that's just a status. Challenge it if you can. If you can't, then let's be a little bit more modest to the public, because it's our duty to give a correct picture. And if the picture is that the singularity is really only a singularity in field space, then we should in one way or another also convey it, and also, take a little bit away of this mysticism that we often convey when we speak about quantum gravity. So, thank you.
Okay, this time we have time for very short questions, but let us first take perhaps a question from the other side, since they might feel a bit left out after.
Yes, we have one.
Are the questions from the other?
Yes, yes. Please.
Okay. In your potential, you show two flat regions. However, the lower flat region is going to zero. Now we know that there is a cosmological smoke vacuum entity, so
Okay.
that being in contradiction to the discovery of the accelerated layers.
Now the potential goes to a constant for chi to 0 and to another constant for chi to the infinity. Now, once you map it to the Einstein frame, actually chi to 0 corresponds to phi goes to minus infinity. So that's why this very flat region comes. It's actually simpler to compute things in the Einstein frame for practical computations. But since it's just a mathematical identity, you can compute it, of course, in every frame. And I have computed it also in this frame where the Planck mass depends on the scalar field, and you get exactly the same answer. So you get an inflationary universe, and this limit phi goes to minus infinity simply corresponds to the limit where this scalar field chi goes to 0, where you have the ultraviolet fixed point.
But the observed vacuum energy is small, but not really.
What? No, I think, no.
Small, not zero.
No, the potential energy you observe is U times k to the 4. That seems very small because this k, maybe it's only 10 to the minus 3 electron volt. But you have to compare it with the Planck mass. And the Planck mass is also very small, because the Planck mass is given by the same scale k. And as a result, the ratio between the potential and the force power of the Planck mass is not a very tiny quantity. It should be small, actually. It should be something like 10 to the power minus 10, because otherwise you get too large density fluctuations. But again, this is a computable quantity. But it's not 10 to the power minus 40. It is a small quantity, hopefully, because if it's order 1, then you predict primordial fluctuations with amplitude order 1, and that's definitely ruled out by observation.
A very short question, please, not more than a...
Yes, on the meaning of the ultraviolet fixed point, for an old argument, there is this old argument for quantum space-time which says you look for where the Compton wavelength and the Schwarzschild radius coincide, and if you use the Newton constant for that analysis, you get the Planck length as the scale where this happens. Now, does your ultraviolet fixed point has the meaning that this argument needs to be revised? And what is the correct version in your picture for this argument? So where does it happen that for a particle or for an object of mass m confined to a very small region h bar over m, when does it happen that the event horizon is at h bar over m? I guess it's going to happen at is it going to happen at a much larger scale? Is this the point? Or can you clarify? This would give me a physical, somehow strangely, the way I think, that would give me a physical meaning to the ultraviolet exponent, which otherwise I feel to get.
Okay, let's go in 2 steps. The first is we want to have a functional integral for quantum gravity, set it up, solve it, see a fixed point, and have a renormalizable theory. The second step is we want to extract now information on momentum dependence, singularity of black holes, things like that. That step is actually much more complicated, because what you have to do, you have now to go with k to 0, include all quantum fluctuations, and look at the momentum dependence of your effective action. So you typically get, for example, a non-trivial graviton propagator, which is curvature scalar times some function of covariant derivative times curvature scalar, things like that, that you have to compute. And that's a hard computation, which in my view has progress, but is not yet at the point where I would make predictions. Some other people make already predictions. But that's the real issue, because at the end, you have to compute an effective action for gravity, from which you can derive quantum field equations, so the relevant equations for cosmology. And then you have to judge about energy scales and so on. I think, unfortunately, there is no real shortcut to that, in my opinion. You really have to do this computation. And a little warning, if you just would say the same thing about QCD, you would start with gluons and quarks, and you may get a lot of, if we would not have known before that we observe hadrons and so on, people would have said, no, that's completely different. Confinement is a completely crazy idea. I think one has to go one step after the other. There will be definitely black hole solutions of this theory, but for example, a judgment, if there is a singularity in the center of the black hole or not, that will depend a lot on what is the form of the full quantum effective action with the momentum dependence. And that's why I am reluctant to make a direct association with K to some physical scale. I think that can only be done a priori. Actually, the way it is done is you run with K to 0, and then if for a certain process you have other effective infrared cutoffs, like coming from momenta, they replace K. But you have for every process to judge that, and this is the standard way how it is done in functional renormalization, if you do it correctly. And this is to a large extent still to be done for questions like black hole singularity or similar questions.
So, sorry we can't take more questions, otherwise I get in trouble with the organizers. So let us thank Christoph once again.
Yes, so now we have the final talk of this joint session. The speaker is going to be Jose Manuel Carmona, who is chair of this cost of action.
Thank you, Julia. Okay, I would like to introduce the network of this cost action to those people who don't know it or even don't even know what a cost action is. This cost association receives funding from the European Commission, and the main tool at what they are called cost actions. Cost means cooperation in science and technology. So the main objective is to form new communities to cooperate in this sense. And I would like to show that the present network has to have new opportunities and new challenges in the field of quantum gravity phenomenology. The title of the action is written in this logo. It was Quantum Gravity Phenomenology in the Multi-Messenger Network. And yes, you can click. Okay, this was reflected in the main aim that defined the cost action. It was to investigate possible signatures of quantum gravity models in the cosmic messengers. And in order to do that, the key point was to establish a close collaboration between different communities, between theoreticians on the one hand, and between experimentalists of the different cosmic messengers, because also these experimentalist communities are rather different and use different techniques, different apparatus, etc. No? So that was the objective, and in fact, we managed to join quite a large network. Presently, there are 325 researchers from 44 countries. 28 of these countries are what are called COST members, and 2 near neighbor countries. And the structure of the action tried to reflect this main aim and this cooperation. Working group 1 is mostly a theory oriented working group. Working group 2 tried to establish a connection between this theory side and the different experimental working groups, which were dedicated to each of the 4 cosmic messengers: gamma rays, neutrinos, cosmic rays, and gravitational waves. We have had during these years, these 4.5 years that the cost action has lasted, a number of different activities. We can remark here what there was a kickoff meeting in Barcelona in 2019 when the action officially started. And then we have had several annual conferences. This is the fourth of them. There have been also some online meetings. I want to remark here this, the one celebrating the 20th anniversary of double special relativity, the discussion session about the LASSO results that were presented in that year, in 21. And we have had some different workshops, and especially 3 training schools, because this was also a main objective of the action, to form a new generation, to train a new generation of researchers, because as you see, the field is quite interdisciplinary. Sorry. Apart from these meetings, there are other tools associated to the post-action. One very important is what is called the short-term scientific missions. We have had 35 of them, and this has allowed researchers to visit other groups and to initiate collaboration, because precisely one of the main goals. Perhaps I want to remark some collaborative projects that have taken place within the action. One is this review paper on quantum gravity phenomenology that Giovanni already mentioned before. There is also a database with experimental bounds on quantum gravity searches. And we are in the process of writing a white paper to conclude the action. And also there is a focus issue in the classical and quantum gravity journal. The lecture notes of the training school are going to be published. In fact, those of the first training schools are already being published in POS. You can access them through the webpage of our action. And apart from this, we have had a number of outreach activities, diversity initiatives, and presence in social areas. Well, all started, as I was saying, with this Barcelona kickoff meeting in 2019. The title of or the main topic of this meeting was this question: what would you like other participants to know about your research? In fact, I think in this meeting, many experimentalists knew for the first time or learned for the first time about DSR theories, because most of analysis, in particular in time delays, have been done in Lorentz evaluation scenarios. Also for theorists, when they learn how experimentalists really do the analysis procedure, for example, in this kind of time delays. This was very timely. I didn't press the right button. Very timely because, in fact, in 2019, in this year, there was this first observation of TeV, tera-electron volt emission, from a gamma ray burst by Cherenkov telescopes by MAGIC collaboration. This was a very important result, where MAGIC collaboration was able to put, thanks to this gamma ray burst, very strong constraints on the scale of quantum gravity, not as competitive in the case n=1 to the gamma ray burst that Giovanni mentioned of 2009, because of the distance. No? It was more near. But the energy of the highest gamma rays, the highest photons were larger than that gamma ray burst. So for the case n=2, for example, the limits were longer, were higher. Thanks to this cooperation between theorists and experimentalists, well, there have been already some DSR modeling, for example, or some proposals for DSR modeling, including the strategy of this first combined LIV study with Cherenkov telescopes, what is called this Gamma LIV working group. Right from the beginning, we were also conscious and started discussing about some critical aspects of these time delays studies. I'm referring here to these intrinsic time delays that well, we have been going on with this discussion. And in fact, yesterday we had several talks concerning this topic and the possible strategies to deal with this. So I want to remark here that all this phenomenology, this LIB and DSR phenomenology involves three levels, no? which refer to the production, to the propagation, and to the detection of these messengers. And this involves astrophysics, this involves theoretical modeling of these effects, and of course experimental analysis techniques. So all of these different subfields are connected and are relevant to put limits on quantum gravity phenomenology. Also, I want to point out that already at the beginning of the action, there were some divergent findings concerning some theoretical analysis which report evidences of some photon time delays. This was also discussed within the action. This met with some skepticism from experimental collaborations, mainly because they are analyses that don't really take care of all the details of the instruments, for example. But also, it was recognized that there are some important points here that, for example, to combine different population of sources to combine studies. So this is something that has been progressing and it is going on. Okay, I would like here, sorry, okay. At this point, I would like to remark that the quantum gravity phenomenology has been usually associated to the Planck scale. But is this necessarily so? In some models, the Planck scale is natural scale, but in some models, one could consider lower scale, which are below Planck scale, perhaps many orders of magnitude below the Planck scale. Which are the limitations of this? Well, in the case of Lorentz-Evans modulation, one can in fact explore the Planck scale. We have sensitivity. This is mainly because of two reasons. Well, if you consider the propagation of cosmic free massless particles, time delays is a mechanism of amplification because of the distance they travel. Also, from the point of view of interactions, kinematic thresholds are modified in LIB in such a way so that the modifications are important when the mass terms are of the order of the new corrections. And this may happen, in fact, at energies much lower than the Planck scale. So that's why we have sensitivity to the Planck scale. But the situation is different. It's completely different in a DSR scenario. Here there is a relativistic principle that, and this changes the situation. For example, concerning the kinematics, there is an extra ingredient, which is the composition law, besides the modified dispersion relation, and that makes low sensitivity to the Planck scale. So that the modifications, the relevant modifications only happen at the scales which are close to this high-net scale. Also, the propagation of massless particles can change and impact they may or may not present time delays depending on DSR model. So one is to take also to have in mind this. Okay, in May 2021, we had this fantastic news. LASSO opened what we can call the PV window to gamma rays. And as I mentioned, our action organized an online session with members of the LASSO collaboration to discuss this. So the main message was that our galaxy is apparently full of neutrons. Well, as Giovanni also mentioned, the key point here is to try to determine the exact location of these sources. Because, for example, because of the universe lack of transparency to high-energy gamma rays, one could not in principle explain within special relativity the arrival of very high-energy photons or PV photons from outside our galaxy. So in fact, this is, offers also some challenges and some opportunities for this community. Some of them are the following. the uncertainties that we have in the photon backgrounds, in the extragalactic background light. Also, that the Lorentz violation studies of this process in which high energy photon loses energy when colliding with this background photon. Well, these studies rely mainly on kinematic modifications, for example, of the threshold of the reaction. But there are other modifications, for example, in the cross-section of this process. And really, there are not exact computations of this cross-section, but some assumptions, some dynamical assumptions are made in this case. Here I want to remark that the superluminal scenario is strongly constrained, not only because this is more favored, but also because the photon becomes an unstable particle. The superluminal scenario, however, could explain these apparent anomalies also that Giovanni referred to. And DSR model here without time delays, in fact, may allow for correction in the transparency of the universe with a high energy scale, which can be significantly below the Planck mass. And this is something that has recently started to be studied. This is just a result from this paper. These results, well, in this plot, you have the quotient between two fluxes. The flux in a DSR model with respect to the flux special relativity. So the flux to special relativity corresponds to this horizontal line. And you see here, for a lambda scale, which is of the order of the end of the spectrum that Lasso measures, that is of the order of PeV, you have corrections to the flux, which, depending on the energy of the photon, may enhance the special relativistic result or maybe suppress it. This is quite different from the LIB scenarios, which is either superluminal or subluminal. So DSR can qualitatively change the behavior also of LIB scenarios. Well, also in 2021, we had what we can say, the evidence, some evidence of the Glasgow resonance. The Glasgow resonance, I recall to you, is the production of a real W with the interaction of an antineutrino with an electron, for example, in the ice. And the ice cube had observed an event at the energy of this resonance, which is 6 PeV. This has been the highest energy neutrino observed by ice cube. Well, this is very relevant, of course, for LIB studies, because in fact, at that time, there was some surprise that we hadn't yet get some signals of this Glasgow resonance, which enhance the cross-section. And in fact, LIB had been proposed as a possible explanation for this apparent cutoff in the high energy neutrino spectrum. This is because superluminal neutrinos can decay. They become unstable and they can decay emitting electron-positron pair or neutrino splitting. That is here, this process here, that is further more neutrinos and with different flavors. One can try to connect neutrinos with gamma rays in this multi-messenger view. And well, as it was mentioned, IceCube and Antares has unsuccessfully tried to find correlations between neutrino events and GRBs. Well, we have seen that some claims about possible correlations with large enough time windows. One, of course, in this analysis should take into account what I said previously about neutrino decays. So one could ask whether this is compatible with the previous neutrino decay process. And for this, recent analytical calculations for neutrino decay widths and the probability distributions for these decays can be relevant, may be relevant to explore these LIB scenarios. This could also modify the standard flavor composition at Earth. So this is another aspect to take into account. We have very recent results from IceCube a couple of weeks ago that in fact seems to establish a correlation between gamma rays and neutrinos at much lower energies. But of course, without the identification of the source, which will be the next challenge. Concerning cosmic rays and ultra high energy cosmic rays, of course, the GSA cutoff was originally measured to provide a test of Lorentz violation. And as Giovanni mentioned before, this has changed a little bit along the years. No? In fact, there are at present several open questions that raise doubts on the sensitivity of this highest part of this cosmic ray spectrum to LIV, which is the origin of the suppression. It is related to the sources, or it is related to the propagation, which is the composition of the ultra-high energy cosmic rays, because the LIV effects depend on the proton fraction. Or are there modifications in the hadronic interactions producing the air showers in the atmosphere that allow to interpret the result? The interactions of the ultra-high energy cosmic rays with these photon backgrounds, in fact, is also a source of cosmogenic photons and neutrinos. And this is another multi-messenger connection that is relevant. This plot is from Michael Reyes' talk yesterday. You see that, well, this is the expected spectrum of these cosmogenic neutrinos that are produced by interactions of ultra-high energy cosmic rays. Well, this is how, for example, this spectrum can be modified in these continuous lines in a scenario of LIV. You see that the change is rather relevant. An enhancement of this peak, which corresponds to the interactions with the ABL, and a suppression, for example, of the peak corresponding to the CMB. This, of course, depends on the model that you are considering, the LIV model that you are exploring. Finally, gravitational waves offer also some complementary information, and this was, of course, the case of the famous gravitational wave and GRB event observed in 2017 that provided insights on fundamental physics, the origin of these short gamma ray bursts, and constrained both LIV models and modified gravity theories. So we are witnessing this dawn of multi-messenger era, with the different messengers will provide complementary information. And also in connection with this, I mentioned these first indications for an nanohertz gravitational wave signal in pulsar timing arrays, very different, that will again open a new window in gravitational wave astrophysics that probably will have implications for quantum gravity phenomenology. So the future prospects, I will end with this. There will be a number of new results and upgrades of instruments in the near future. So just to mention, there are a few: CTA, LASO, Kentrinet, ISP second generation, Mascaran detectors, LIGO, and other gravitational wave detector upgrades. So they will deepen in the new astrophysical windows, which have been recently opened. And the main point is that they will improve the sensitivity to the fluxes, and it will be necessary to just explore this quantitatively. So to pass really to a precision era in quantum gravity phenomenology. Well, the experimental advances will have to be accompanied by theoretical developments, of course, in the formulation of which are the phenomenological consequences of LIV and DSR models. In particular, what I mentioned about the phenomenological sensitivity to high energy scale, which is many orders of magnitude below the Planck mass. This is possible in a scenario of default relativistic invariance and may be relevant in some models where the Planck scale is not the effective scale, but it combines with further parameters of the theory. Depending on the magnitude of this low energy scale, this may be relevant even in particle physics experiments, and I think we will have some talks about that in this conference. And I want to stress here that the deformation of relativistic invariance is even conceptually very different from LIV. It lies, doubly special relativity, it lies beyond the framework of effective theory. And even a different notion of locality may be behind of some conceptual issues of DSR that I think they are not still completely solved, like this source-of problem, what is called the spectator problem. Well, finally, these LIV and DSR scenarios give different phenomenology for the different cosmic messengers, so a multi-messenger analysis will be necessary to distinguish them as explanations of anomalies. And the cooperation between different communities will, of course, will continue to be relevant for that. So this is the end of the action, but I hope this is not the end of this cooperation. In fact, my view is that the action, what it did was to put the necessary seeds for this cooperation that will be important in the near future. Thank you very much.
We have time for a couple of quick questions. We may give priority to the conference in Nijmegen, if there is any.
Any questions here? There is one question here.
Yes, go ahead.
Well, my question will be the following. Whether it is possible to describe double special relativity within the standard formalism used within the Lorentz symmetry breaking. Because as far as I know, in many cases, the double special relativity describes breaking of Lorentz invariance, but in another language, in language of dispersion relations. Dispersion relations can be derived from some certain Lagrangians. Whether, what is your opinion about this idea, this similarity of approaches?
Yeah, so double special relativity contains an essential ingredient beyond a modified dispersion relation. This essential ingredient is the modified composition law. In fact, I would say that even at the beginning of DSR theories, more weight was given to this modified dispersion relation. I think the essential ingredient is the modified composition law. One can even have DSR models which have the standard dispersion relation of special relativity, but do not have, I mean, they contain necessarily a modified composition law. So this is something that distinguishes completely the LIB scenario and cannot be described. So that's why they are conceptually different and also phenomenologically. There is not a common framework for them.
Any other questions here? No? So we can hand it back to you. So no other questions from Nijmegen?
Yes, is there any quick question from here? Yes, there.
When you contemplate a DSR framework with a scale much lower than the Planck scale, of course you confine yourself to DSR scenarios without invariant dispersion, because otherwise they would be falsified. But and then I understand, but should we not be concerned that somewhere else, not in the invariant dispersion, this deformation at such low scale would, I mean, how far have you explored possible other, I know it's like looking everywhere, but is there some, or at least maybe the opposite direction, did you see some other invariant dispersion would be a key vulnerability because the data have high quality, but you protect yourself from, I mean, your scenario is protected from that by not having invariant dispersion. But is there some other thing that in your experience we should look at as a possible say pathology produced by new physics at a scale much lower than the Planck scale?
Yeah, my view is that we need to look to interactions. I mean, propagation is perhaps not important, and this is a view, perhaps a new view that can be that one can have about DSR. That perhaps DSR is a new, is a way, an effective way to take into account, for example, a loss of locality of interactions. So in this sense, yeah, of course, the effects, you see some differences with respect to special relativity, only with the energy, one of the energy which is relevant is of the order of this lambda, this high energy scale. For much lower energies, you don't see anything. So yes, in some sense you lose this predictive power if this high energy scale is very large, but in the other, because well, one could have deviations from special relativity at energies which are attainable at present, and you don't have constraints
Okay, so I think we have to close.
Yes.
Yes, sorry. One last quick question from here and then we close. Sorry, I didn't see.
In other fields, like when in the searches for dark matter, there is people are plotting a plot of mass and cross sections in different experiment, different tests, are putting limits, and I would have hoped that this is not a question, it's a call for what this community should do. If you take something very simple like this dispersion relation correction, plots like this, combining different data from different experiments, and take them seriously. Take them seriously, meaning that if there is some region which is ruled by one experiment, and you want to suggest an effect in from, let's say, a threshold barrier, but there is a region in a region which is ruled by other experiment, don't suggest.
Yes.
So I think that, yeah.
Sorry, it's a very interesting idea. Is that you see, even for example, in this plot from dark matter, there are regions which are excluded by some experiments, but there are still some, for example, these gamma regions, which are inside a region which is excluded by other experiments, because you can always find some way out. For example, in this case, you can have interactions with different nuclei. So if the experiment is not exactly the same, it's not considering the same kind of interaction, you can always go back. Or for example, in the case of action plots. In action plots, there is the action band, which is the preferred theoretical model for actions. But of course, one can go beyond that and say, okay, perhaps we don't have real actions, QCD actions, but we have action-like particles. And when you open this, you need then to explore different regions. So it is not I would say it is not as simple as to consider that this is, for example, cosmology. Cosmology can rule out several regions, but still you need to explore this experimentally, because there may be some caveat in these arguments. So I think the idea is very interesting to have these plots with the different bounds. But I would say, yes, one has to take it seriously, but also cautiously.
Okay, so we really have to close the session here. So thank you to the other conference. I think this was a very nice and successful experiment. Yes, and okay. Thank you to everyone.
And a big thanks to all the speakers for the morning session once again.